How does gravity link apples and planets? What secrets ride on starlight? Do light and gravity speak for the universe? In a quiet orchard at dusk, a gentle breeze rustles the leaves. An apple lets go of its branch and falls to the soft ground without a sound. This simple act is guided by an invisible pull that we rarely stop to notice. You feel that same pull every moment. It's what gives weight to your body as you stand, what makes your arms drift downward if you raise them and let go. It is gravity, a silent force that draws all things toward each other, keeping us firmly in Earth's embrace. Each footstep you take is a small surrender to gravity. When you lift your foot, you briefly defy this pull, and when you set it down, gravity welcomes you back. This unseen force choreographs a quiet dance between your body and the earth. You push off the ground and arc forward. Gravity gently guides you down again. Step by step, you are actually falling, in a controlled way, into each new footfall. In this gentle fall, we call walking. Gravity gives us stability and rhythm. Gravity's hush extends far beyond our steps. Picture the ocean stretching out to the horizon, its surface rising and falling in a slow, steady rhythm. The tides that sweep in and out along the shore are gravity's handiwork as well. The moon, hanging bright in the night sky, tugs imperceptibly at the oceans. Though you cannot feel this pull in your own body, the vast seas respond, lifting slightly toward the moon. When the moon climbs high overhead or slips to the opposite side of the world, it draws the water up, causing the tide to rise. Between those times, the water gently recedes again. From the beach, it feels as if the ocean is breathing. Inhale, exhale, 2 high tides and 2 low tides each day, a steady pulse orchestrated by the moon's quiet gravity. Not only the oceans, but even the ground beneath us moves to gravity's subtle timing. The solid earth itself flexes just a little, swelling and sinking each day as the moon passes overhead. We never notice this solid earth tide under our feet. It's only a few inches at most, but it's there, a faint echo of the lunar pull that moves entire seas. Everything, from the grains of sand to the crust of the planet, answers the moon's call in its own small way. The gravity that we know best is the Earth's pull on us and on the things around us. But gravity is universal. Every object with mass reaches out to every other. High above us, the moon is falling too. It is perpetually falling toward Earth, caught by Earth's gravity. Yet the moon also moves sideways fast enough that it never crashes down. Instead, it falls around the Earth. This is what an orbit truly is, a continuous fall, curving endlessly around our planet. The moon's quiet descent, balanced by its forward motion, becomes a graceful loop that repeats month after month. Our Earth, in turn, is falling around the sun in a cosmic dance guided by gravity. Just as the moon orbits us, we orbit the sun, held by the sun's immense but silent gravitational embrace. We do not sense this motion. It is as gentle as a cradle. Year after year, Earth traces its path around our star, a journey of about 584 million miles, all due to the sun's pull. The same force that guides our steps and stirs the tides also holds Earth and the other planets in their great, looping paths through space. It's humbling to realize that an apple dropping to the ground and the moon circling Earth are governed by the same law of nature. Centuries ago, a young scientist sitting under an apple tree is said to have witnessed a falling apple and wondered if that very same force extended all the way to the moon. He imagined the moon as a kind of falling apple, forever falling, but never reaching the ground. He was right. The invisible thread of gravity links the apple to the moon, the earth to the sun, and the sun to distant stars and beyond. Even when we cannot see the force itself, we see its gentle choreography everywhere in the movements of nature. Gravity works its enchantment in silence. There is no sound to Earth's pull, no light from this force, and yet it quietly dictates the structure of our world. It keeps our atmosphere wrapped around us and holds us to our path around the sun. In the still of the night, when you drop a pebble into a pond and see the ripples spread, remember that an unseen force is pulling that pebble downward. That same force is, at this very moment, guiding the moon through the sky and holding you firmly to the ground as you watch. It's a comforting thought. Gravity gently cradles us every second of our lives, an ever-present but silent companion. As we gaze up at the moon on a clear night, bathed in its soft glow, we're witnessing more than just reflected light. We are also feeling the steady, invisible tug that the moon and Earth share. This quiet gravity connects us to our closest celestial neighbour in both seen and unseen ways. And under that moonlit sky, by the whispering waves, we sense the dual presence of light and gravity. The moon's light reaches our eyes across 250,000 miles, and the moon's gravity reaches across that same distance to stir the seas at our feet. One acts as a gentle messenger we can see, the other, a persistent pull we can only feel by its effects. In the harmony of a calm night, they work together, light and gravity, silently shaping our experience of the world. Now, as the moon casts its silver path on the water, it invites another thought of a different kind of journey. The light we see from the moon is itself on a voyage, traveling an invisible route from the sun to the moon and then to our eyes. This soft illumination spilling across the waves is a reminder that there are other subtle forces at play, carrying messages across the darkness. As gravity keeps the moon in its orbit and the tides in motion, light carries the moon's image to us. In this gentle interplay of forces, we find ourselves ready to follow the next whisper in our cosmic story. The journey of light, the soft messenger across space and time. Light moves through the darkness like a gentle whisper, carrying secrets from one place to another. Imagine standing under a night sky sprinkled with stars. The faint starlight that reaches your eyes left its home years, decades, or even millennia ago. Each pinpoint of light overhead is a traveler, a messenger from a distant past, bringing you a story. Perhaps one star's light began its journey before you were born and is only now arriving, quietly telling you of that star's long-ago state. Another star's photons might have set out when ancient civilizations on Earth were just beginning to flourish, and only tonight do they complete their long voyage. In this moment, you are connected to far-off suns by threads of light, threads that bridge time and space in perfect silence. Light is a most patient courier. Day after day, the sun floods our world with bright rays that took about 8 minutes to reach us from the solar surface. When you feel the sun's warmth on your face on a clear morning, you are feeling the touch of photons that departed the sun moments ago, each carrying a bit of our star's energy across 93 million miles of space. This warmth is a gentle reminder of the sun's constant presence and generosity. And in that sunlight also come clues. The color of the sky, the sparkle on water, the rainbow after a storm. All are messages delivered by light, telling the story of our atmosphere and our world. At dusk, as the sun sets, the sky's colours shift to soft oranges and pinks. These hues are a final message from the departing daylight, scattering through the air to paint a gentle goodbye until tomorrow. When night falls, we trade the sun's direct glow for the ancient starlight that has been travelling across the galaxy. In the darkness, you might even glimpse the faint, milky band of our galaxy's own light, a collective glow of uncountable distant stars whose individual voices blend into a soft silver ribbon across the sky. Each tiny glimmer in the night is evidence of light's tireless journey. Not all light is visible to our eyes. Around you, an invisible symphony of light waves is constantly playing. The warmth you feel from a fire or from the sun is the work of infrared light, which you cannot see but can sense as heat. In the stillness of the night, a radio can play music carried by radio waves, another form of light with wavelengths so long and gentle that they pass through walls and air with ease. Even the remote control for your television sends commands using invisible infrared light. These varied forms of light, infrared, radio, ultraviolet, X-rays, carry different stories. Some tell of warmth, some of cosmic events like exploding stars, which emit powerful X-rays that astronomers catch with special instruments. We live immersed in a sea of light, much of which we never directly perceive, yet it surrounds and informs us every moment. Consider the moon hanging low on the horizon on a quiet evening. Its pale glow is not its own, but borrowed sunlight reflected back to us. That gentle moonlight is the sun's message, softened and relayed by the moon. When you bask in moonlight, you are actually bathing in second-hand starlight from our own star. And what a delicate, silver-tinged message it is, bright enough to cast shadows, yet soft enough to feel almost magical. This light allows us to see the outline of clouds at night, the shimmer of a path on the water, and our own faint shadows dancing under the moon. It connects us to the lunar landscape as well, revealing the moon's craters and plains in a subdued glow. Through moonlight, we glimpse another world while standing on our own, all by the grace of reflected light. Every ray of light, whether from the sun, the moon, or distant stars, carries information. If you were to split sunlight with a prism, you'd unveil a hidden rainbow, colours that tell the tale of elements in the sun's atmosphere. Starlight, when captured and studied, reveals what stars are made of and how they move. In this way, light is a faithful messenger, conveying the secrets of the cosmos. It travels for years or centuries through the void, until finally it brushes against an eye or a telescope here on Earth. In that brief moment, the long journey is complete and the message is delivered. The universe uses light to communicate, sending pictures and whispers of distant places into our own sky. This soft messenger moves at the fastest speed possible, yet to us, its journey often feels slow and patient. We cannot see it racing through space, only arriving long after its departure. Think of the nearest star beyond our sun, Proxima Centauri. Its light takes over 4 years to get here. If you gaze at that star tonight, you are seeing it as it was 4 years ago. For stars farther out in our galaxy, the light can be hundreds or thousands of years old by the time it reaches us. And the light from galaxies beyond our own can travel millions or even billions of years before arriving at Earth. The farthest galaxies we glimpse are sending us light that began its journey before our planet even existed. That ancient light crosses unfathomable gulfs, quietly traversing the cosmos, until one night it finds its way to someone's eyes or a camera's detector. In the stillness of an observatory dome or the quiet of your backyard, an interstellar traveler finally arrives, bringing with it a piece of cosmic history. Yet for all its speed and reach, light is gentle. It doesn't shove or shake as it passes. It simply illuminates. A photon from a star will glide through space without losing its way, unless something like a planet or a cloud of dust crosses its path. And even then, light often finds a way around obstacles, bending in a planet's atmosphere to produce the soft colors of sunrise and sunset, or scattering in mist to form halos around the moon. In every such interaction, light leaves a signature, a tale told in color, brightness, or pattern, waiting for those who know how to read it. As you stand under the night sky, bathed in the faint glow of countless stars, consider the quiet triumph of those photons that have completed their long journeys. So much could have happened to them on the way. They might have been absorbed by dust or scattered by intervening clouds. But here they are, gentle arrivals from across the galaxy, reaching your eyes at last. They carry no sound, no scent, only the subtle message of illumination, which your mind then transforms into wonder and understanding. With the dawn, the stars' messages fade in the overwhelming radiance of our sun once more. But even daylight is filled with wonder. The sun's rays bring life to our planet, coaxing plants to grow and warming the oceans. That daily light is as common as breathing to us, yet it remains a miracle of communication across space. The sun speaks to the earth in light, and the earth responds with life in return. As we reflect on how light connects us with the universe, we remember that the moon's gentle glow, linking our gaze to the night ocean, is both a gift of light and a reminder of gravity's reach. The moon's presence is felt not only in its reflected light, but also in the tug that raises our tides. When the moon slips below the horizon and the sky grows darker, the ocean's pulse continues its quiet cycle, guided by that unseen pull. Light and gravity each play their part, one visible, one invisible, both essential. Now, shifting our focus from the sky to the water's edge, we follow that silent tug to witness the ceaseless rise and fall of the tides and the slow turning of our world under the influence of its celestial companions. By the shore of a tranquil bay, water laps at your feet and then slowly retreats. You stand quietly, feeling the wet sand sink slightly under you as the water pulls back. The ocean is alive with a gentle rhythm, rising and falling as if it were breathing in its sleep. These are the tides, the great, slow pulses of the sea, caused by the steady tug of our moon and the distant sun. If you watch the shoreline over the course of hours, you'll notice the water inching higher up the sand, covering rocks and shells that were dry moments before. The tide is coming in. After reaching a peak, it will pause briefly at high tide, then gradually begin to slip back out, revealing the damp sand once more. This cycle repeats itself about twice each day, governed mainly by the moon as Earth rotates beneath the moon's gravitational pull. When the moon is overhead on your side of the world, or directly beneath your feet on the opposite side, its gravity draws the ocean water slightly toward it, causing a bulge, a high tide. There's another high tide on the opposite side of Earth at the same time, and in between, the water is drawn away from those areas, creating low tides. As our planet turns, these bulges of water move around the globe, and coastal areas experience their regular rhythm of 2 high tides and 2 low tides each day. This tidal rhythm is not perfectly in step with our 24-hour day, because the moon is also moving in its orbit. Each day, the moon rises about 50 minutes later than the day before, and the tides follow along, arriving later each day. If you visit the beach at the same time every morning, you'll find the tide has shifted, perhaps a little higher, perhaps a little lower, because the ocean is keeping time with the moon. It's as if the sea is listening to a different clock, one set by the moon's journey around Earth. The sun plays a role in this ocean ballet as well. Though farther away, the sun's gravity is powerful, and it tugs on our oceans too, adding its influence to the tides. When the sun and moon align, during new moon when the moon is between Earth and sun, or during full moon when they are on opposite sides of Earth, their gravitational pulls combine. The ocean feels a stronger tug in roughly the same direction, and the high tides climb a bit higher than average, while low tides dip lower. These are called spring tides, not for the season, but for the idea of springing forth. At those times, the ocean's breadth deepens, reaching farther up the shore and farther out to sea. Conversely, when the moon is at first or third quarter, positioned at a right angle relative to the sun's pull partially cancels out the moon's. Then we see neap tides, with highs a bit lower and lows not as low. It's a gentler breathing of the ocean, as if the sea is taking smaller sips of air. Whether spring or neap, the change is modest, perhaps a difference of a few additional feet of water. But to those who watch the tides, the pattern is clear. The sea follows the cosmic dance steps laid out by its partners, the moon and sun, never missing a beat in this eternal waltz. Tides don't only affect the ocean. The solid Earth is involved too. The entire planet experiences tiny distortions due to these gravitational pulls. Beneath your feet, the ground itself is rising and falling by inches in response to the moon and sun. We are usually unaware of this Earth tide. It's far too slight to feel and happens very slowly. But with precise instruments, scientists can measure the crust lifting and settling twice a day. Even the most solid ground has a subtle elasticity under the influence of gravity. It's a reminder that nothing is truly rigid or still when it comes to planetary motions. Everything yields, however little, to the cosmic rhythm. Over long spans of time, the moon's tug on those tides has another effect. It acts as a brake on Earth's rotation. As the ocean waters are pulled by the moon, friction along the seafloor ever so slightly slows Earth's spin. The change is infinitesimal in the span of a human life. A day lengthens by only a couple of milliseconds in a century. But across millions of years, those tiny drags add up. In the age of the dinosaurs, for instance, a day was a bit shorter than our current 24 hours. The moon is gradually receding from Earth as well, inching away over time due to this tidal interaction. These changes happen so slowly that they're almost like a dream of the distant future and past, rather than anything we would notice day to day. Still, it's fascinating to know that the quiet push and pull between Earth and Moon is reshaping the length of our days and the breadth of our Moon's orbit, ever so gently. For now, we live with the comforting regularity of the tides. Many coastal lives are attuned to this cycle. Fishers launching their boats at high tide, tidal pools refreshing their hidden worlds of starfish and anemones with each flood, and mangrove forests breathing in seawater twice daily. In centuries past, people who lived by the sea used the predictability of tides to guide their activities, even weaving them into folklore and calendars. The oceans rise and fall became a familiar heartbeat of coastal existence, a subtle clockwork of the shore. Standing there with the waves swirling around your ankles, you can feel connected to something vast and ancient. The rhythm that lifts the entire ocean is the result of celestial bodies moving in the sky above. It's a beautiful thought that the moon, glowing softly overhead, and the distant sun, whose light still hangs in the twilight sky, together orchestrate the ebb and flow at your feet. The earth turns, the moon circles, the sun shines, and the water responds in kind. This seamless connection between sky and sea is calming, a reassuring pattern in a world of constant change. As the tide gently goes out once more, leaving behind glistening sand and tiny bubbles of foam, you step back from the water's edge. Overhead, the moon and stars continue their silent vigil. You've felt the touch of their gravity in the moving sea, even if indirectly. Now your attention drifts upward and inward to another invisible influence surrounding our planet. Just as the ocean has an unseen force guiding its rhythm, the very air and sky around us are guarded by a hidden magnetic veil. With the roar of the ocean fading behind, we turn to this next mystery. Earth's magnetic field, an invisible shield and guide that envelops us all. High above, in the polar night, curtains of green and violet light silently ripple across the sky. You watch in awe as these auroras ebb and flow, shimmering like gauzy drapes in a celestial breeze. What you're seeing is a rare glimpse of Earth's invisible shield made visible. Normally, the magnetic field around our planet is undetectable to our eyes, but when charged particles from the sun slam into it, they light up the upper atmosphere in these waves of color. This is Earth's magnetic veil, an unseen force protecting us every day. Earth is like a giant magnet. Deep within its core, molten iron churns and flows, generating a magnetic field that stretches far out into space. From the South Pole to the North Pole, loops of magnetic influence extend and encircle our world. We cannot feel it directly. This field passes through us and around us without a hint. Yet it quietly directs the needles of compasses, always guiding them to point north and south. For centuries, travelers and explorers relied on this invisible guide to navigate the seas and wilderness. A simple compass in your hand, its needle quivering toward north, is a small, everyday magic courtesy of Earth's magnetic field. This magnetic field is not just a guidepost, it's also a guardian. The sun continually emits a stream of charged particles known as the solar wind, which blows outward through the solar system. When these particles reach Earth, they encounter our magnetic field and are mostly deflected, forced to flow around the planet like water around the bow of a ship. In this way, Earth's magnetism forms a protective bubble called the magnetosphere, which shields us from much of the solar wind's potentially harmful radiation. On days when the sun is stormy, throwing off great eruptions of charged particles, solar flares and coronal mass ejections, our magnetic shield flexes and strains under the impact. Most of the particles are still kept at bay, but some spiral down along the magnetic field lines toward the poles, colliding with atoms high in our atmosphere. When they do, the sky ignites in those beautiful auroras, nature's own neon sign tracing the shape of our magnetic field. The lights swirl and dance, but eventually the storm passes, and the shield holds strong. We seldom think about this magnetic cocoon around Earth, because it is usually invisible and silent. But life on the surface benefits from it every moment. If Earth lacked this shield, the solar wind could strip away our atmosphere over time, as it likely did to our neighboring planet Mars long ago. With a weak or no magnetic field, Mars was vulnerable to the sun's particles, which gradually whisked much of its air and water into space. Here on Earth, our magnetic field helps keep our atmosphere intact and our planet hospitable. Animals, too, quietly tune in to Earth's magnetism. Migrating birds navigate along invisible magnetic pathways during their long journeys. Sea turtles, born on a beach, may find their way back decades later, in part by sensing Earth's magnetic signature, unique to that stretch of coast. Even tiny creatures like certain bacteria contain particles of magnetite that align with the magnetic field, helping them tell up from down in murky water. This hidden sense, almost magical to us, guides countless beings in their wanderings. If you close your eyes and imagine the space around our planet, try to picture the magnetic field as a vast, delicate spiderweb of energy. Near Earth's surface, it emerges at the south, loops through space, and re-enters at the north. It forms a teardrop-shaped bubble, compressed on the sunward side and stretched into a long tail on the night side. Within this bubble, we are snug and protected, most of us never realizing it's there. Only when a compass needle turns or the polar sky glows do we catch hints of this enveloping presence. Earth's magnetic field does change over time, drifting and even reversing polarity every so often on a geologic timescale. But these shifts happen slowly over thousands of years, and the shield itself does not vanish even then. It merely reorganizes. Right now, somewhere in the southern Atlantic Ocean, Earth's magnetic field is slightly weaker, in an area scientists call the South Atlantic Anomaly. Satellites passing through that region experience a bit more radiation from space due to the weaker shielding there. But on the ground, we still are safe, wrapped in our planet's magnetism. Such nuances of the field are a reminder that even our protective veil has its subtle ripples and wrinkles. Still, through it all, Earth's invisible shield carries on guarding us. The next time you see a picture of Earth from space with its glowing auroras, or hold a compass in your hand, remember that you are witnessing a sliver of this unseen force. It's comforting to know that far above, beyond the blue sky, an invisible magnetic embrace is capturing solar winds and cosmic rays on our behalf, making our world a little calmer and safer. It's another silent guardian in our daily lives, as dependable and quiet as gravity or the light of the sun. Invisible forces like magnetism surround and protect us, operating quietly in the background of our lives. They remind us that so much of reality is hidden from our direct senses. Even something as fundamental as time has subtle secrets. We take time for granted as a constant beat, but under certain conditions, time itself stretches and shrinks ever so slightly. Before us lies another quiet mystery of the everyday cosmos, the gentle, imperceptible malleability of time as we live and move on this earth. In a quiet laboratory, two perfectly synchronized clocks tick side by side, their hands moving in unison. Now imagine taking one of those clocks up to a high mountain while leaving the other at sea level. After some time, if you bring them back together and compare, you would find a tiny difference. The clock that went to the mountaintop will have ticked slightly ahead. In other words, time ran just a touch faster for the clock on the mountain than for the one by the sea. This isn't a trick of the clocks, but a reality of nature. Time itself flows a bit differently depending on altitude. High above sea level, where Earth's gravitational pull is a tad weaker, time loosens just the slightest bit, passing marginally quicker. This effect is called gravitational time dilation, a consequence of Einstein's theory of relativity. Gravity doesn't just pull on space, it tugs on time as well. Down in the depths of a gravity well, like at sea level, closer to Earth's massive bulk, time moves more slowly compared to higher up. The difference is extremely small in everyday terms. A person living their entire life on a mountaintop might gain only a few dozen extra microseconds of life compared to a twin at sea level. It's so slight that we'd never notice without ultra-precise instruments. Yet the difference is real, proven by sensitive atomic clocks and experiments that carry clocks on airplanes and up tall buildings. Time, that seemingly rigid flow, reveals itself to be gently elastic under the influence of gravity. Motion, too, can alter the pace of time. If you take one of those precise clocks on a fast jet around the world, it will tick ever so slightly slower than an identical clock left at rest. This is time dilation due to speed. The faster you move through space, the slower you move through time, from the perspective of someone stationary. Again, in our daily lives, these differences are vanishingly small. We don't feel time pause or lurch when we drive a car or fly in a plane. But sensitive instruments and careful experiments have confirmed that it happens. Astronauts orbiting Earth in the International Space Station, for example, experience time just a hair differently than we do on the ground, because they are moving very fast and also a bit farther from Earth's gravity. Their personal clocks run at a slightly altered rate. Over 6 months in orbit, an astronaut might age a few milliseconds less than if they had stayed on Earth. When they return, they have lived almost imperceptibly fewer heartbeats than those of us planet-bound. They won't notice it, but the universe does. These minute differences in the flow of time only matter in extreme precision or over long periods. But they illustrate a profound truth. Time is not absolute. It can stretch or shrink in the presence of motion and gravity. We live our whole lives under these subtle effects without ever feeling them. Only with the advent of precise technology did humans discover that the clocks in GPS satellites high above Earth tick faster than clocks on the ground. To give us accurate location data, those satellite clocks must be adjusted to account for both their speed and their higher orbit, where gravity is weaker. Thanks to Einstein's insights, engineers knew to make these corrections, and that's why the GPS in your phone can guide you so unerringly. It's a quiet nod to relativity in everyday life. Someday in the future, if humans travel at speeds close to the speed of light, or venture near a massive object like a neutron star, time's flexibility will become more than just a tiny curiosity. A space traveler might experience only a few years on a high-speed journey, while decades or even centuries pass on Earth. It sounds like science fiction, yet it is simply the dramatic limit of the same gentle effect that makes mountain clocks tick faster and moving clocks tick slower. Time would become a river with different currents for those in different voyages. This realization turns what was once purely philosophical, the malleability of time, into a tangible aspect of cosmic travel. Think of time as a gentle stream flowing through a vast landscape. In most places, it flows at a steady pace that we all agree on. But here and there, the stream runs a little faster or slower around a massive mountain of gravity or under the push of a swift journey. The changes are subtle ripples, not roaring rapids, at least in the environments we know. Only near things like black holes or at speeds approaching light do these ripples swell into waves that we could really notice. In our familiar realm, time's flexibility is a hidden grace, affecting us but never disturbing our daily rhythm. Late at night, when you glance at a clock and see the seconds steadily advancing, it's intriguing to ponder that somewhere far above, time is moving just a touch faster, and in a jet plane, it moves a touch slower. We are talking differences of billionths of a second, nothing that would change the cadence of our lives. But knowing this can shift your perspective. Even something as fundamental as the passage of time has a supple, responsive nature. It bends graciously to the circumstances of speed and gravity, like a dancer adapting to the music of the cosmos. Our journey through hidden forces has shown that even time can quietly bend. Still, these shifts in time remain invisible to us, detectable only with careful measurement. In our day-to-day world, we notice none of it. And just as there are things happening in time that we can't feel, there are also physical travelers moving through us, and the Earth completely unseen. Every second, the cosmos sends forth ghostly particles that slip through walls, through oceans, through our very bodies without a trace. We turn now to these phantom visitors, starting with some of the most elusive of all, the neutrinos, the ghosts that pass through walls. All around you, all the time, an invisible rain is falling. It's not water or light. It's a rain of tiny, ghostly particles streaming through space. These particles, called neutrinos, come from the nuclear reactions in the hearts of stars, including our Sun, and from other energetic events in the cosmos. Every second, tens of trillions of neutrinos pass through your body. For perspective, in a single second, more neutrinos will pass through you than the total number of stars in the Milky Way galaxy. Yet you remain completely unaware of this cosmic deluge. They pour down through the sky in daylight and continue through Earth during the night, traveling straight through the planet as if it were a mist. To a neutrino, the Earth is almost as insubstantial as a cloud. Neutrinos are often called ghost particles, and for good reason. They hardly ever interact with ordinary matter. A wall, a mountain, or an ocean might as well be clear glass to them. In the time it takes you to blink, countless neutrinos have passed through the wall behind you, through your body, and then down into the Earth. Nearly all of them emerge on the other side of the planet without ever touching anything. It's as if they exist in a parallel world, one that overlaps with ours but rarely intersects it. If you held out your hand, trillions of neutrinos would glide through it each second, and you'd never feel a thing. Given their abundance, one might wonder how we even discovered neutrinos, if they are so aloof. The answer lies in patience and clever detection methods. Deep underground, in abandoned mines, or under mountains, scientists have built vast detectors, tanks filled with ultra-pure water or special liquids and lined with light sensors. Down there, far from interfering cosmic rays, these detectors sit in darkness, waiting. When a neutrino happens to hit an atom in one of these tanks, a faint flash of light is emitted. It happens extremely rarely, but when it does, the sensors catch the brief glow. In this way, human beings have learned to sense the unsensible. We've caught the ghost in the act, if only a few times. The first time this was achieved, it confirmed what many had suspected. Neutrinos are real and constantly around us. Even now, each day in these detectors, a handful of neutrino interactions might be recorded out of the vast hordes passing by. It's like trying to catch a single drop from a flood by waiting with a thimble. Yet that handful of detections is enough to begin to piece together their story. We have learned, for instance, that the sun produces an immense number of neutrinos, illuminating us with an invisible light. We've also captured neutrinos from a star that exploded in a nearby galaxy. In 1987, detectors buried underground recorded a burst of neutrinos from a supernova in the Large Magellanic Cloud, a small neighbor galaxy, hours before the exploding star's light reached Earth. It was an early whisper of that stellar cataclysm. We have also detected neutrinos from more familiar sources, such as nuclear reactors on Earth. These sightings are like postcards from otherwise hidden realms of the universe. Neutrinos rarely leave a trace, but when they do, they have tales to tell. Because they pass through so much untouched, they carry pristine information from where they originated. A neutrino that reaches an underground detector from across the galaxy arrives almost exactly as it was when created, unaltered by intervening matter or fields. In this way, neutrinos are messengers of events we might otherwise never know about. They slip out of the core of the sun and inform us about the nuclear furnace within. They escape from distant supernova explosions and whisper to us about the death throes of stars, sometimes even before we see the explosion's light. They are quiet heralds of cosmic happenings. To imagine the nature of a neutrino, think of a restless phantom passing through a busy market without touching a single person, unseen and untouched. That is how neutrinos move through the universe. They are so nearly nothing that they almost aren't there. And yet, because they are created in such abundance, they are everywhere. At this moment, a ghostly wind of neutrinos is blowing through the very room you sit in, though you feel no breeze. It's a humbling realization that our world is not as solid and separate as it appears. On a subatomic level, it's more like a sieve with endless holes through which these tiny ghosts travel. As we marvel at these phantom particles, it's worth remembering that not every visitor from the cosmic deep is so retiring. Some come crashing into our world and announce themselves with energy, yet even these make little sound in our everyday experience. While neutrinos slip through without a stir, other particles streaking in from distant stars do collide with the Earth, sparking cascades of invisible fire in the high atmosphere. We live under a constant gentle drizzle of these cosmic rays. They too are mostly unseen and harmless at the surface, a silent rain of energy from the stars. Now let's turn our attention to this quiet cosmic rain and the subtle marks it leaves on our world. Far above us, in the thin upper air, a single subatomic particle from a distant galaxy slams into the atmosphere at fantastic speed. In that instant, it shatters into a shower of smaller particles and photons, a tiny cascade of energy spreading out like an invisible fireworks display. This event is a cosmic ray collision, one drop in the continuous drizzle of high-energy particles that rain down on Earth from space. It happens countless times each day, yet we go about our lives unaware of these silent fireworks overhead. Cosmic rays are fast-moving particles, often protons or atomic nuclei, that originate in some of the most energetic places in the universe. Some are hurled out by the sun during solar flares, but the most powerful ones arrive from beyond our solar system, perhaps from exploding stars, supernovae, or tumultuous regions around black holes. They travel across the void for years or millennia, until, by chance, they encounter our little planet. Over a century ago, a scientist set out to test the origin of this mysterious radiation. In 1912, Victor Hess carried instruments in a balloon high into the atmosphere. As he rose miles above the ground, he noticed that the levels of ionizing radiation increased rather than decreased. In the calm, thin air 5 kilometers up, he realized that something from space was raining down on Earth, causing these readings. His daring high-altitude experiment was the first confirmation of cosmic rays, discovered in the hush of the upper sky. On extremely rare occasions, a cosmic ray of astonishing energy strikes. In 1991, for example, an ultra-high-energy proton was detected over Utah, with energy so great, scientists nicknamed it the "Oh my God" particle. It carried about as much energy as a fast-thrown baseball concentrated into a single subatomic particle. We may encounter just one such particle in a century across a few square miles. What cosmic engine could hurl something so small with such force? We can only speculate. Perhaps the furious environment around a supermassive black hole, or the remnants of an exceptionally powerful supernova. Yet, when this lone cosmic bullet hit our atmosphere, it announced itself only through the quiet glow of its particle shower. Even the most dramatic cosmic arrivals can come and go without any fanfare to our senses. We might call this a rain of fire because of the immense energy cosmic rays carry, but it's a rain in which the fire is quenched long before it reaches us. High above, that energy is absorbed in the atmosphere, producing nothing more than a slight ionization of the air and a few secondary particles that swiftly decay. On rare occasions, during a particularly strong solar storm, the flux of cosmic particles increases enough that we measure a bit more radiation at airplane altitudes, or see brighter auroras dancing farther from the poles. But even then, on the ground, life continues quietly under the protective sky. Over eons, cosmic rays have subtly influenced our world. They contribute to the formation of certain isotopes in the atmosphere, like the carbon-14 used in radiocarbon dating, tying cosmic phenomena to the story of life on Earth. There are even theories that cosmic ray fluctuations might have minor effects on cloud formation or climate over long timescales. Whether or not that's true, one thing is certain. Cosmic rays are a link between us and the wider galaxy. They are pieces of distant stars and galaxies reaching us, a reminder that we are not isolated from the cosmos. Each particle that arrives is a traveler from afar, ending its long journey in our skies. Each cosmic ray that falls to Earth is a direct messenger, a straight-line traveler that arrives at our doorstep. But not everything in the universe comes to us so directly. Some wonders are hidden behind veils of darkness or distance. To perceive those, nature has another quiet trick. Gravity itself can act as a lens, bending the path of light and allowing us glimpses of the otherwise invisible. In the next part of our journey, we will explore how mass can curve light's journey, revealing secrets that lie out of reach of even our most powerful telescopes. It's a gentle bending of perception, a soft gravitational lens that lets us see what we otherwise could not. Picture yourself gazing at a distant landscape through a window with old, wavy glass. The scenery beyond appears distorted. Straight lines bend into gentle curves, and small details can seem stretched or duplicated. In space, gravity can play a similar trick on the light traveling past massive objects. Light, usually so straight-laced, will have its path curved by the presence of mass. A massive galaxy or cluster of galaxies creates a warp in spacetime, causing the light from objects behind it to detour and converge towards us in surprising ways. The result is a natural cosmic lens. This gravitational lensing was first confirmed over a century ago. During a solar eclipse in 1919, astronomers measured the positions of stars near the eclipsed sun and found that they appeared slightly shifted from where they would normally be. The sun's gravity had bent their light just enough for us to notice, validating Einstein's theory that space and time can be curved by mass. That bending was minuscule, but in the vast cosmos, with far greater masses and distances, gravitational lensing can create remarkable sights. Multiple images of the same distant quasar, rings of light encircling galaxies, aptly named Einstein rings, and arcs of light that are actually the stretched images of even more distant galaxies behind a closer cluster. Modern telescopes have captured these ethereal distortions. Some galaxy clusters, when photographed, reveal faint smears and loops of light curving around them, the telltale signatures of gravitational lensing. In those images, each arc or ring is the light of a faraway galaxy, magnified and deformed by the intervening mass. It's as if gravity has taken a paintbrush to the canvas of the sky, delicately stretching and bending the light. These natural lenses not only create beauty, but also act as cosmic magnifying glasses, enabling us to study the early universe in ways otherwise impossible. Imagine a galaxy cluster sitting between us and a faraway galaxy. The cluster's enormous gravity wells, mostly invisible dark matter, along with the visible galaxies, warp the space around them. As light from the distant galaxy passes by the cluster, it follows the curved space, bending inward and focusing toward Earth. An observer here might see the single distant galaxy smeared into arcs, or even appearing as multiple faint copies around the cluster's edges. This cosmic mirage is not a trick of our optics, but a real distortion of space itself, acting like a vast, gentle glass lens in the universe. Gravitational lensing serves as a powerful tool for astronomers. It can magnify distant, otherwise unreachable objects, making them visible to our telescopes. Thanks to lensing, we have observed galaxies from the early universe that would be too faint to detect without this natural boost. We have also used lensing to map the unseen, the mysterious dark matter that emits no light of its own. By studying how light bends around galaxy clusters, scientists can infer where the hidden mass lies, painting a picture of the invisible scaffolding of the cosmos. In effect, gravity's soft lens lets us see the invisible by its influence on the visible. Even on a smaller scale, gravitational lensing shows up. When a star passes precisely in front of another more distant star from our viewpoint, the closer star's gravity can act like a lens on the background star's light. For a short while, the distant star appears to brighten as its light is focused toward Earth. This phenomenon, called microlensing, has even led to the discovery of planets. A planet orbiting the nearest star can tweak the lensing effect in a telltale way, revealing its presence. All of this unfolds without a sound, without a flash, just the steady, subtle brightening and dimming of starlight as unseen objects drift in front. It's another quiet testament to how the universe communicates through gravity and light. To our eyes, a gravitational lens isn't something we sense directly. Instead, we see its results in photographs from telescopes or in carefully measured changes in starlight. But conceptually, one can imagine standing in a vast, dark hall of mirrors in space, where massive objects gently bend and redirect beams of light. There is elegance in this silent shaping of light. No physical lens is present, only the curvature of space-time itself, invisible, yet capable of producing an image. It reminds us that space is not a static void, but a malleable fabric that responds to mass. Under the stars on a clear night, we might wonder what lies behind the darkness and how much we cannot see. Gravitational lensing gives us one answer. Even the darkness can be a window, opened by gravity's touch. It allows us to peer a little further, to notice a dim glow that is not where it appears to be, but rather an echo of something far behind. In the grand tapestry of the cosmos, gravity subtly weaves connections between things, bending straight lines into arcs that link the seen with the unseen. As we contemplate these arcs of light and what they reveal, we prepare to journey to the edge of our own cosmic neighborhood, where the sun's influence fades and a new kind of boundary awaits. Imagine drifting far beyond the orbit of Pluto, into a realm where the sun is just a particularly bright star among many. Out here, the warmth of the sun has dwindled to near nothing, and darkness is deep. Yet, even in this cold expanse, the sun makes its presence known. A faint breeze of charged particles, protons and electrons streaming outward from the sun's corona, blows through space. This is the solar wind, the breath of the sun, expanding in all directions. It has been travelling outward since it left the sun, gradually thinning as it fills a bubble around our solar system. This immense bubble carved out by the solar wind is the heliosphere, and it defines the space where the sun's influence is still stronger than that of the interstellar medium beyond. Closer to the sun, here on Earth, we are firmly inside this bubble. The solar wind, along with the sun's magnetic field, envelops us and even helps shield us from some high-energy cosmic radiation. But as we travel outward, the solar wind that once blew fiercely near the sun becomes a gentle puff. There comes a point, far past the outer planets, where this outward breeze can push no further against the thin gas between stars. At that boundary, the solar wind's strength drops, and the particles from the rest of the galaxy begin to dominate. This is the edge of the heliosphere, known as the heliopause, a kind of cosmic shore where the sun's influence ends and the interstellar ocean begins. For a long time, this boundary was theoretical. No human-made object had ever been there to feel what it's like. That changed when the Voyager 1 and 2 spacecraft, launched in 1977, finally reached those distant waters decades later. In 2012, Voyager 1 experienced a sudden change in its environment. The particle sensors observed the solar wind practically vanish and the flux of cosmic rays from outside surge. It had crossed the heliopause, becoming the first probe in interstellar space. Voyager 2 followed in 2018, confirming the milestone. These tiny ambassadors, each carrying a golden record of Earth sounds and greetings, now drift in the space between stars, still reporting back faint signals. They felt the sun's breath fade behind them, and the cooler, older breath of the galaxy take its place. The heliosphere is not a perfect sphere. It's shaped by the sun's motion and by external pressures. It likely has a tail streaming behind and a more compressed front where we plough into the oncoming interstellar medium. But however it's shaped, it's our sun's domain, a cocoon inflated by our star's energy. Inside it, the planets and countless comets reside, all bathed in the solar wind and protected from some cosmic rays. Far beyond the planets, a distant reservoir of icy bodies, known as the Oort cloud, extends tens of thousands of times farther from the sun than Earth. Those comets are bound by the sun's gravity, but drift far outside the heliosphere, on the outskirts of our solar family. The sun's gravitational influence reaches them across the dark, even as its solar wind does not. Light and gravity, in their own ways, tie the solar system together well beyond the heliopause, but the sun's protective wind and magnetism stop here at this cosmic shoreline. To put it poetically, we have been travelling this whole time under the sun's wing, and now we stand at the edge of its nest. Beyond lies the galaxy at large, where our star's light and wind are just one among billions of others. Here at the boundary, one can almost imagine a change in the wind's sound. except there's no air to carry sound, only a shift in the type of particles sailing by. The concept of wind takes on a new meaning when it's made of atoms and charged particles in the vacuum of space. But the analogy holds. There is a breeze from our sun, and beyond it, the combined, faint breath of countless other stars. Standing at this cosmic coastline, we can appreciate how far the sun's influence reaches, and how finite it is. Roughly 120 times farther from the sun than Earth is, the heliopause marks the end of one chapter and the start of another. Within that boundary, the sun's warmth and particles shape the environment. Beyond it, the galaxy's vast sea takes over. In a sense, the heliosphere is our solar system's gentle shield. Much like Earth's magnetic field is our planet's shield. It deflects some cosmic rays. It carves out a space for our star, and it gradually sways like a giant windsock in the interstellar breeze. As we contemplate this frontier, it's awe-inspiring to think that all of our history, everything we've ever known, has unfolded under the protective blanket of the heliosphere. Only now are our instruments and imaginations crossing beyond it. The cosmos stretches out infinitely beyond this point. Yet even here, at the threshold of interstellar space, we find a connection back to our sun. The particles and fields may be changing, but the sun's light can still reach, and its gravity still holds the solar system family together from afar. Here, at what is essentially the outer shore of our solar system, we pause. We have followed gravity, light, magnetism, time's quirks, ghostly particles, cosmic rays, and the sun's far-reaching breath, all the subtle threads that shape our cosmic neighborhood. Ahead lies the vast unknown of the galaxy, with even stranger and more powerful hidden forces. Enormous black holes that bend spacetime violently, dark matter that holds galaxies together, energy fields that fill the vacuum. Those realms call to us, but they are stories for another night. For now, we linger in the calm, knowing that we have traced the unseen contours of our own corner of the universe. In the quiet of this moment, floating at the edge of the sun's domain, we feel the gentle balance of all these forces, quiet, persistent, and wondrous. Our journey continues onward, but for tonight, we rest under the same stars, grateful for the invisible guardians and messengers that have silently guided us here. In the silent darkness between the stars, giant clouds of gas and dust drift quietly. They are so cold and so empty by earthly standards that they seem inert, yet they are the cradles of new suns. Some stretch for dozens of light years, harboring mass as great as millions of suns, spread out in an invisible mist. Dust grains in these clouds block the starlight beyond, rendering the cloud's interior black and hidden. Inside this darkness, something delicate is taking shape. For ages, the cloud drifts, seemingly unchanging. But it is not perfectly still. Gentle turbulence stirs within, forming wispy filaments and knots of slightly denser gas. Now and then, an outside influence, perhaps a faint shockwave from a distant explosion, or the tidal push of a passing cluster, jostles the cloud's serenity. In those denser patches, gravity gains a small advantage, tugging neighboring material closer. Very slowly, a part of the cloud begins to cave in under its own weight, marking the quiet start of a star's birth. In these murky depths, gravity works quietly and relentlessly. Every sparse atom feels a faint tug from its neighbors. Slowly, over countless years, the cloud starts to gather inward. As pockets of gas grow denser, they warm up, but the cloud has a way to shed this warmth. The gas and dust release their heat as faint infrared light that slips away into space. This cooling allows the collapse to continue, letting gravity tighten its grip, step by step. Threaded through this cloud are ghostly magnetic fields, so slight that they barely stir a compass, yet they influence the dance of the gas. For a time, the magnetic field lines and the mild pressure in the cloud hold up against gravity, slowing the collapse. But as the cloud cools and more matter piles inward, even these faint fields yield. The cloud fragments into smaller clumps, each a budding star cocoon. Deep within one of these shrinking globules, densities and pressures climb higher, preparing the stage for a new kind of fire to awaken. At the heart of one shrinking globule, the material grows ever hotter and denser as it falls inward. The hydrogen gas is squeezed so fiercely that its temperature soars to millions of degrees. In this extreme furnace, the atoms are completely stripped into electrons and bare nuclei. The building blocks of those nuclei, the protons, race chaotically at incredible speeds through the plasma. Normally, protons electrically repel each other, refusing to get too close. But now gravity's relentless compression forces them into near collisions, despite their mutual push. When two protons are finally shoved close enough together, an extraordinary thing happens. A different fundamental force seizes the moment. The strong nuclear force locks the two protons together, overcoming their electric repulsion. In that instant, the two protons fuse into a single helium nucleus. This process releases a burst of energy in the form of high-energy light. Not just one pair, but countless protons begin to collide and fuse in the dense core, creating a flood of energy. The young star's heart has ignited at last, glowing with its first internal fire. That flood of new energy pouring from the core creates a pressure that pushes outward. The inward collapse that gravity started is suddenly opposed by an expanding glow from the center. The protostar's contraction slows, then halts, as a new balance is reached. The raging heat at the core forces the surrounding gas to expand slightly, and the star stabilizes. What was once just a cold, collapsing fragment has become a newborn star. Deep inside, nuclear fusion burns steadily, and a shining star emerges from the darkness. Inside the newborn star, a quiet contest is underway. Gravity has not disappeared. It continues to pull every bit of the star inward, trying to squeeze it smaller. But an equal force now pushes back from the star's core. The intense heat from the nuclear fire creates a high pressure in the star's center. The hot, glowing plasma pushes outward, and countless photons, particles of light, flood outward as well, exerting a gentle pressure of their own. For the first time, the inward pull and the outward push are balanced. The star exists in a state of peaceful equilibrium, neither collapsing nor expanding, but holding steady in a delicate standoff. This equilibrium is not fragile, it is dynamic and self-correcting. If the core burns a touch too hot and produces slightly more energy, the star's outer layers swell outward, cooling the core just enough to calm the reactions. If the core cools and output drops, the star's layers shrink inward, heating the core and boosting fusion again. In this way, the star regulates itself like a cosmic thermostat, keeping its luminosity remarkably steady. From afar, it shines with a gentle constancy, barely flickering over millennia. The furious processes within are hidden beneath a placid glow that seems timeless. For many stars, this tranquil standoff can endure for millions or even billions of years. Our own sun is one such star, having burned in stable harmony for nearly 5 billion years. Throughout this vast span, it has provided steady warmth and light, hardly changing from one age to the next. The star's interior stays hot and bustling, but to an outside observer, it appears serene and almost unchanging on human timescales. Yet this calm interior belies the activity at the surface. Now that it is stable, the young star begins to influence its surroundings. It pours energy and matter into space beyond itself, and those stellar outflows will slowly sculpt the cosmic neighborhood around the star. The newborn star now stands revealed, and it immediately begins to change its surroundings. Intense starlight streams outward in all directions, and with it comes a steady wind of particles blowing off the star's surface. This stellar wind is like a gentle cosmic breeze, carrying charged particles into space at hundreds of kilometers per second. Over time, the wind and radiation push away the remaining shreds of the cloud that once enveloped the star. A bubble forms around the star, a hollow cavity in the nebula, as the nearby gas and dust are swept aside. What was once an opaque womb of dust becomes a clear space, allowing the star's light to escape into the wider galaxy. Magnetism also plays a role in this cosmic sculpting. The young star's magnetic field extends far into the space around it, twisting and arching through the hot gas. Along the star's poles, these field lines help launch narrow jets of material. Twin streams of gas erupt outward from the north and south poles of the star, shooting into the surrounding darkness. Each jet carries energy and matter away from the star, boring tunnels through the remaining cloud. These jets are like cosmic chisels, carving straight through the nebula and clearing paths for the starlight. In time, they can extend light years from the star, fading into space as slender, glowing streaks. The once chaotic stellar nursery is now being gently reshaped by these forces. The star's radiation ionizes the surrounding gas, causing the nebula to glow softly in hues of red and violet. Pillars and wisps of denser gas linger at the edges, silhouettes against the new light, slowly eroding under the stellar onslaught. What was a dark, cold cloud has transformed into a glowing cradle of youth, a nebula lit from within. In images of the cosmos, such scenes appear as breathtaking clouds with hollowed centers and delicate, sculpted edges, all crafted by the quiet breaths of newborn stars. Through wind and magnetism, the star has become an artist, subtly carving its environment over thousands of years. But even as the star quietly sculpts its surroundings, the clock of its life is ticking. This peaceful scene will not last forever. In the distant future, the star will exhaust the fuel in its core and lose its internal balance. When that moment comes, the star's gentle breath will turn into one last violent exhalation. It will be a colossal explosion that reverberates across space, sowing the seeds of new creation. A star's death arrives in an instant compared to its life. One moment, the star's core can no longer support its own weight. The next, the core collapses and then explodes outward with unimaginable force. In a brilliant flash, the star that once gently lit its corner of the sky outshines an entire galaxy. The supernova erupts with a burst of light and energy so intense that for days or weeks it can be seen across cosmic distances. What was a single point of light swells into a sphere of searing plasma racing outward. For a brief time, night turns to day for any worlds near this dying sun, as a wave of radiance and high-energy particles floods space. Then, as suddenly as it came, the initial flash fades, leaving behind the expanding debris of the star. Deep inside that explosion, alchemy is at work. In the star's final moments, new elements are forged in the high-pressure furnace of the blast. Gold, silver, uranium, and dozens of other heavy elements suddenly come into being, created by the extreme energy of the supernova. At the same time, all the elements that were formed during the star's life, carbon, oxygen, iron, and more, are hurled out into space. The contents of the star's core, which a moment ago were locked away, are now strewn across the cosmos. These ejected atoms mix with the interstellar gas, enriching it. In this single event, the raw materials for planets and life are scattered far and wide. The calcium in our bones, the iron in our blood, the gold in our jewelry. Much of it was forged in a supernova like this, long ago, and cast into space by the stellar blast. Meanwhile, the shockwave from the explosion surges outward through the galaxy's gas. It's like a cosmic tsunami, ploughing into any nearby clouds of interstellar gas and dust. When the wave hits those clouds, it compresses them, squeezing the gas tighter. In some cases, this sudden squeeze can spark the birth of new stars, as sections of the cloud collapse, just as our star's nursery once did. Even where it doesn't trigger new stars, the supernova's blast stirs the galactic medium like a spoon swirling soup, mixing the rich elements into the cosmic broth. In the aftermath, an expanding shell of glowing gas, a supernova remnant, spreads out as a lasting echo of the explosion. Tangled filaments of cooled debris mark where the star's remains are colliding with the surrounding medium. Over centuries and millennia, this shell will disperse and blend with the interstellar clouds. But the disturbance it caused can set into motion a new cycle of star formation. From the death of one star come the first whispers of new beginnings. For in the debris and dust of this explosion lie the seeds of future worlds, waiting to coalesce around newborn stars. Around a newly formed star, a broad disk of dust and gas spins like a great cosmic carousel. It is the leftover material from the star's birth, flattened into a rotating plane by the star's gravity and by its own motion. In this disk, fine grains of dust made of rock, metal, and ice circle quietly in countless numbers. From afar, the disk might appear as a subtle band of darkness silhouetted against the star's light, or it might glow faintly in infrared, hiding its treasures from direct view. Within this thin disk, the conditions are calm and cold, a stark contrast to the raging fusion in the star's core. Yet, it is here in this dusty ring that the next act of creation begins. At first, the dust grains are like powder, drifting in a vast, shallow sea. They occasionally collide as they orbit, but at such low speeds that they gently stick together rather than shatter. Tiny electrostatic forces, the same that make a balloon cling to a sweater, help the grains clump. Bit by bit, the dust gathers into larger particles. What were once motes, the size of smoke particles, grow into flecks like sand, then pebbles. In the silence of space, these minuscule mergers happen unceasingly, but almost imperceptibly. Over thousands of years, grains build up into pebbles, and pebbles into rocks large enough to hold themselves together. As the pieces get bigger, the process accelerates. Once rocks reach the size of boulders or small mountains, their gravitational pull becomes significant. These larger fragments, called planetesimals, start to attract each other from a distance. They collide and merge, forming still bigger bodies. A few kilometre-wide objects slowly snowball into dozens, then hundreds of kilometres across. Each merger releases energy, heating the growing proto-world slightly, but there is no one around to hear or see it. The growth of a planet is almost silent and unseen. One by one, these embryonic planets sweep up the remaining debris in their path. In time, most of the dust and gas in the disk is gone, incorporated into the star, locked into planets, or blown away by the star's wind. What remains are a handful of new worlds orbiting their sun. Some may be small, rocky planets close to the star, forged from metal and stone. Others farther out might be giant balls of gas, formed where ices were plentiful and could quickly build large cores to gather thick atmospheres. Each planet circles in the same direction, following the original rotation of the disk, like dancers moving to a tune long faded. The once chaotic cloud has organized itself into a planetary system, a new set of worlds quietly taking shape in the twilight of the dissipating disk. Yet the positions of these young planets are not set in stone. Even after the disk has vanished, subtle forces continue to act. Gravitational tugs between planets and the lingering pull of any remaining gas or debris can nudge the worlds from their original orbits. Slowly, almost imperceptibly, planets begin to drift through the darkness, wandering away from the places they first formed. In the aftermath of planet formation, a planetary system may appear settled, but subtle forces are still at play. Over immense spans of time, whole worlds can drift from the orbits where they first formed. Astronomers have discovered giant planets orbiting extremely close to their stars, so-called hot Jupiters, which likely formed much farther out in colder regions. The existence of these wandering giants was our first clue that planets can migrate. Something, unseen and gradual, must have pulled or pushed these planets into new orbits, long after they were born. During the early epochs, a young planet still interacts with the gas disk that birthed it. If the planet is massive enough, its gravity creates spiral waves in the remaining gas, like a boat making ripples on a pond. Those waves tug back on the planet, robbing it of energy and angular momentum. Slowly, the planet spirals inward toward the star, riding the wake of its own disturbance. Alternatively, under certain conditions, a planet can migrate outward, drawn by particular resonances in the disk's flow. In either case, the movement is slow, a drift that might carry a world millions of kilometers over many thousands of years. To any creatures that might one day inhabit such a world, the migration would be imperceptible, a silent journey through the dark. Even long after the gas is gone, planets can continue to wander due to their mutual gravities. In multi-planet systems, the worlds tug on each other whenever their orbits bring them into alignment. Usually these tugs are slight, causing small oscillations in their paths. But occasionally, two giant planets might fall into a gravitational interaction that isn't stable. Their repeated encounters can fling one planet inward or outward. In dramatic cases, one planet might slingshot the other entirely out of the system, exiling a world to the lonely interstellar void. The remaining planets then shuffle into new positions, finding fresh orbits where the gravitational tug-of-war settles down again. There are hints that our own solar system underwent such migrations in its youth. The current spacing of the planets and the distribution of small bodies, like the asteroid belt and the distant Kuiper belt, suggest a past reshuffling. The giant planets may have moved from their original positions, disturbing those belts of debris and perhaps causing an era of heavy bombardment on the inner planets. Over time, they settled into the stable, nearly circular orbits we see today. Such migrations might be a common phase in the life of planetary systems, an adjustment period where planets trade energy and settle into lasting harmonies. In the end, gravitational interactions that once caused chaos can also lead to order. Some planets settle into resonant orbits, where their gravitational tugs on each other create a regular, repeating pattern rather than random disturbances. In these resonances, the planets stabilize each other's paths and establish a peaceful rhythm. Stability can emerge from the tumult as worlds find their balance. And it's not only planets that dance into equilibrium. Stars themselves can be bound in elegant gravitational duets. Many stars are born as twins, locked in orbit around each other, their mutual gravity tying them together in a cosmic balance. Not every star is alone in the cosmos. Many are born as pairs, or even triplets, siblings bound together by gravity from the moment they ignite. Imagine two stars orbiting around a common center, each held in the other's gravitational embrace. These binary stars perform a slow, celestial dance, circling an invisible point in space between them. Neither star crashes into the other, nor do they drift apart, as their mutual gravity keeps them in a perpetual balance. In this cosmic pas de deux, each star counterbalances the other, moving faster when they draw closer and slower when they separate, always remaining gracefully in step. Such a partnership can endure for billions of years. The two stars might be very different. One could be large and bright, the other smaller and dim, yet they revolve together faithfully. Their orbits are usually stable and predictable, tracing the same ellipses over and over. In a quiet binary system, the gravitational pull each star feels from the other is like a constant centripetal force, guiding it around and around without end. The result is a cosmic balance, a stable two-star system shining together in unison. If these stars have planets, those worlds might orbit one star or both, experiencing two dawns and two dusks in their sky. But even with the complexity of two suns, the overall system can remain in steady harmony, as long as the orbital dance remains orderly. Stability through gravitational balance is a theme that extends beyond binary stars. Within planetary systems, moons and planets often find rhythm in their orbits as well. A clear example is found around Jupiter. Its moons, Io, Europa, and Ganymede, are locked in a resonance with each other, orbiting in periods that form a simple 4:2:1 ratio. For every 4 laps, Io makes around Jupiter, Europa makes 2, and Ganymede makes 1. This resonance keeps their gravitational pulls in sync, preventing destabilizing tugs and ensuring they never all align in a troublesome way. In effect, they take turns tugging on each other in a regular pattern, which maintains long-term stability. Similarly, in some distant planetary systems, astronomers have observed chains of planets in resonance, each planet's orbit timing perfectly with its neighbors. These resonant dances are nature's way of creating order from potential chaos, allowing multiple bodies to coexist in a system without colliding or drifting randomly. In the grand scheme, these balanced dances, whether two stars circling or planets in resonance, impart stability to their local cosmic neighborhoods. Each harmonious system is like a microcosm of order in the vast galaxy. And as we zoom out further, we discover that even our galaxy itself is governed by gravitational patterns and streams. The stars, gas, and dust of the Milky Way all orbit the galactic center, following paths shaped by an even larger, invisible structure. Much as planets follow the gravity of stars, stars follow the gravity of the galaxy. They move collectively in sprawling spiral arms, which are themselves giant waves of density moving through space. Now, leaving behind the scale of individual stars and systems, we widen our perspective to trace the enormous galactic currents that guide stars and nebulae along their journey around the Milky Way. Our Milky Way galaxy is a vast disk of stars and gas, tens of thousands of light years across, turning majestically like a giant pinwheel. It rotates in a stately manner, the inner regions making a circuit faster than the outer ones, but all bound together by gravity. Our own Sun, for example, takes roughly 230 million years to complete one orbit around the galactic center. As the galaxy spins, it doesn't move as a solid whole. Instead, it behaves like a swirling fluid, with stars and nebula orbiting along lanes shaped by the galaxy's mass distribution. Through long exposure telescopic views, we see this disk is patterned with spiral arms, luminous bands of stars, and glowing gas that wrap around the galaxy's core like the arms of a slow-turning spiral sea. These spiral arms are not rigid structures, but rather regions where stars and gas crowd a bit more densely, a pattern moving through the galaxy. As clouds of gas orbit the galactic center, they periodically encounter an arm. Upon entering an arm, the cloud experiences a gentle squeeze. The higher density and gravitational pull in the arm act like a wave pushing against the cloud, causing it to slow down slightly and compress. This compression is a mild shock, enough to trigger new star formation within the cloud. Consequently, the spiral arms are dotted with bright, newborn stars and glowing nebulae, marking where the gas has recently been stirred into creating stars. After the cloud passes through the arm, it re-expands somewhat and continues on its orbit, leaving behind those new stars to light up the arm from within. Between the spiral arms lie calmer regions of the galactic disk. Here, the density is lower, and gas and stars drift in a more spread-out fashion. These are like the gentle interludes in the galaxy's grand symphony, broad, quiet stretches where relatively little star formation takes place. In these inter-arm spaces, cold hydrogen gas can flow more freely, forming vast, diffuse streams that slowly circle the galactic center. One might imagine them as calm rivers of gas, weaving through the landscape of the galaxy. They carry the raw material for future stars, slowly feeding the spiral pattern. When one of these languid streams eventually meets a spiral arm, or is disturbed by a passing star cluster, its serenity may end as it gives birth to new stars. But until then, the gas glides along, unhurried and largely unseen, maintaining the galaxy's enormous cycle of matter. Standing back to observe the Milky Way as a whole, we see a living system shaped by invisible forces. Gravity's pull, organizing billions of stars, waves of density steering the flow of gas, and the feedback of countless stellar lives, enriching and stirring the galaxy's contents. The hidden influences we've followed, from the quiet pull of gravity in dark clouds to the rippling density waves of spiral arms, all play a role in crafting the tapestry of our galaxy. Yet, the Milky Way is but one swirl in a vast cosmic ocean. Beyond our galaxy, immense structures and forces bind galaxies together and send them drifting through space. The same laws of physics, the same unseen cosmos of forces, extend to the scale of galaxy clusters, cosmic filaments, and the expanding universe itself. Our journey through hidden forces is far from over. We pause here, poised at the edge of our galactic understanding, ready to venture outward into the even larger mysteries of the cosmos. In the quiet depths of space, far from any city lights, a spiral galaxy rotates in the darkness. This shimmering island of stars turns gracefully like a colossal pinwheel suspended in the cosmic void. As our perspective drifts high above its flat disk, we watch the outer stars orbiting around the galactic center. There's a gentle whisper in their motion. They circle surprisingly fast, as if compelled by a hidden hand. Those stars on the galaxy's fringe do not slow down as expected. Instead, they maintain speed as if something invisible is pulling them along. In our own solar system closer to home, distant planets creep around the sun more slowly than the inner ones, their pace dwindling with distance. This pattern is a familiar rhythm set by gravity. The farther a planet is from the sun, the weaker the pull, and the more leisurely it moves in its orbit. But out here in this faraway galaxy, the rules seem different. Even at the very edge of the starlight, where the glow of stars thins into darkness, the outermost stars keep pace with those nearer the core. It is as though an unseen gravity grips them, preventing them from drifting away into space. This observation is a quiet clue, a subtle hint that something massive yet invisible surrounds the galaxy. Decades ago, under the stillness of night skies, astronomers trained their telescopes on galaxies like this and measured the speeds of stars and gas swirling within. What they found was unexpected and profound. Instead of a graceful slowing at the outskirts, they saw nearly flat velocity curves. The outer stars were moving as swiftly as those closer in. These galactic rotation curves, as they came to be known, whispered of an unknown influence. It was as if each galaxy was immersed in a vast halo of matter that could not be seen, gently tugging on the stars from the shadows. One astronomer, Vera Rubin, spent many quiet hours analyzing the light from distant galaxies in the 1970s. As she and her colleagues mapped the rotation of galaxy after galaxy, the pattern repeated itself across the cosmos. Time and again, the stars far from the galactic centers moved too quickly to be held in place by the gravity of visible matter alone. The findings were met with both intrigue and skepticism. Could there really be something immense and invisible enveloping every galaxy? The notion was bold. Perhaps a new kind of matter filled the darkness, exerting gravity, yet emitting no light. This invisible mass soon went by an evocative name: dark matter. Dark matter cannot be seen directly. It neither shines nor absorbs light. Yet, in the stillness of space, its presence is felt through the gentle pull it exerts. It acts as a hidden scaffold, holding galaxies together from the inside out. Without it, those fast-moving outer stars would simply fly off, flung away like water droplets from a spinning wheel. But they do not escape. Instead, they keep circling, bound by the gravity of this unseen mass. In the elegant dance of a galaxy's rotation, dark matter reveals itself only by its effect, a ghostly conductor guiding the cosmic ballet. As more galaxies were examined, the evidence quietly mounted. Virtually every spiral galaxy observed showed this same puzzling behavior in its rotation. The visible stars and gas were only part of the story. Far beyond the glittering spiral arms, an enormous quantity of something unseen had to be present. Each galaxy, it seemed, was cradled in a diffuse halo of dark matter, extending well beyond the starlight, like a cocoon of gravity enveloping the luminous disk. These halos are transparent and silent, yet they outweigh the stars by several times over, forming the bulk of each galaxy's mass. This realization was transformative. It meant that the cosmos contains far more than meets the eye. Perhaps 5 times more matter in this dark form than in all the glowing stars and gas. With this dark component, galaxies hold together. Without it, they would tear themselves apart over cosmic time. The swift stars at the fringes provided the first convincing whisper of this cosmic secret, hinting that an invisible form of matter dominates the dynamics of galaxies. At first, the idea of such unseen mass was met with cautious wonder. Some proposed that maybe our understanding of gravity needed adjustment at these scales, rather than invoking a new kind of matter. But as the years passed, multiple lines of evidence began to point to the same conclusion. Something real, with gravity, lurks in the dark. The rotation curves were a crucial clue, but not the only one. Beyond individual galaxies, in the vast communities of galaxies bound together by gravity, the whispers of unseen mass grew into a chorus. Galaxies are not solitary wanderers. They congregate in great clusters containing hundreds or even thousands of members. Within those crowded clusters, the motions of galaxies and the glue holding them together also betray a hidden influence. The mysteries hinted at by a single galaxy's rotation become even more pronounced on these larger scales. If a spiral galaxy's gentle curves whispered of dark matter, the grand dance of galaxy clusters would soon speak even louder, providing further evidence that most of the universe's mass is indeed invisible. Drifting further out into the cosmos, we find ourselves among a great cluster of galaxies. Here, hundreds of galaxies gather together, bound by their mutual gravity in a vast cluster that spans millions of light years. In this crowded cosmic city, galaxies large and small glide through the cluster's center, like fireflies caught in a gentle swarm. To the eye, one sees myriad galaxies shining, but much like the solitary spirals, this entire cluster holds a deeper mystery. The galaxies move as if pulled by a stronger gravity than the visible matter alone can provide, hinting again at a mass that isn't there for us to see. Nearly a century ago, an astronomer named Fritz Zwicky first took note of this conundrum while studying a distant cluster known as Coma. He measured the speeds of galaxies within that cluster and found them racing about much faster than expected. By all rights, at those breakneck speeds, the galaxies should have escaped the cluster's grasp and flown apart into space. Yet the cluster persisted, as though some hidden glue was binding it together. Zwicky boldly suggested that there must be a tremendous amount of unseen mass lurking in the cluster, far more than all the stars could account for. He called it dark matter, matter that does not shine, yet has weight, an invisible bulk holding the cluster in its gravitational embrace. For decades, Zwicky's idea remained on the fringes, intriguing but unproven. Later observations began to strengthen his case. In these colossal clusters, scientists found another clue, a faint, pervasive glow of X-rays. Though invisible to our eyes, sensitive space telescopes revealed that clusters are filled with a vast reservoir of extremely hot gas that permeates the space between galaxies. This gas is heated to tens of millions of degrees and emits X-rays as it glows. It turns out that this thin, searing gas outweighs all the galaxy's stars put together, an unexpected treasure trove of ordinary matter hiding in plain sight, detectable only in high-energy light. However, even this discovery did not solve the mystery of the cluster's mass. When astronomers added up all the matter they could see, the shining galaxies and the X-ray glowing gas, the total still fell far short of the gravity needed to hold the cluster together. The galaxies were moving too quickly, the hot gas too loosely confined, for the visible mass alone to keep them bound. The sums simply did not add up. Something else, something enormous and invisible, must contribute the majority of the cluster's weight. Once again, the finger pointed to dark matter as the missing ingredient, providing the extra gravity. Imagine floating in the middle of such a galaxy cluster. All around, galaxies drift like lanterns in a vast, dark sea. You feel the tug of gravity from all sides. the pull of a deep gravitational well carved by the cluster's mass. Yet much of that mass is invisible. The bright galaxies are like the tips of icebergs in a sea of unseen matter. Beneath the surface of visibility, an ocean of dark matter holds sway, accounting for most of the gravity you feel. It is a silent presence, as real as the stars, binding the cluster together from the shadows. To weigh a cluster like this, astronomers use the galaxies themselves as test particles, measuring their motions to gauge the cluster's gravitational pull. They also read the telltale heat of the hot gas. The higher the temperature of that X-ray gas, the stronger the gravity needed to contain it. Both methods tell the same story. The required gravitational pull far exceeds what known matter can supply. In cluster after cluster observed, from nearby groups to those billions of light years away, the pattern repeats. Each cluster seems to be draped in an immense cloak of dark matter, outweighing the visible matter by several times. These colossal dark matter halos of clusters tie together the fate of hundreds of galaxies at once. Within them, galaxies move like leaves, swirling in a vast eddy, their paths governed by the curvature of spacetime created by the cluster's unseen mass. If we could see this dark matter directly, a cluster might appear as a giant, faint cloud enveloping the galaxies, extending well beyond the cluster's luminous core. The ordinary matter, stars and hot gas, collects in the deepest pockets of this invisible cloud, much as dust might settle into the low places of a landscape shaped by an unseen scaffold. The more we studied these clusters, the clearer the picture became. In a typical galaxy cluster, scientists estimate that the mass in dark matter is several times the mass of all the ordinary matter combined. Perhaps 5 out of every 6 parts of matter in the cluster is this dark component. That means only a small fraction of the cluster's gravity comes from things we can directly see. Such an imbalance might seem astonishing, but it makes sense of the observations. The fast galaxy motions, the hot gas confined by gravity, and the sheer stability of the cluster all point to a huge reservoir of hidden mass. Without it, the structure of these immense clusters simply could not hold together over billions of years. This revelation turned clusters of galaxies into important laboratories for cosmology. By observing these massive systems, scientists could probe the properties of dark matter on the largest scales. No longer was dark matter a mere hypothesis hidden in the equations. It was a tangible presence inferred from multiple, independent clues. The motions of galaxies, the temperature of intergalactic gas, and later even the bending of light, all told a consistent story. Dark matter is not a minor anomaly, but a major constituent of our universe. In shining clusters scattered across the sky, nature was offering clear evidence that most of the matter binding those clusters was invisible to our telescopes, yet undeniably real through its gravity. Having weighed the substance of clusters through motion and heat, astronomers sought a more direct sightline into the unseen. If gravity from dark matter could hold galaxies and gas in its sway, perhaps it could also bend light, passing through its grasp. The idea of using light as a probe, watching how background galaxies are distorted by a cluster's gravity, gained traction. And sure enough, when they looked closely, they saw the faint shapes of distant galaxies smeared and stretched around massive clusters. These cosmic mirages were the result of light rays being deflected by the cluster's gravitation, much as predicted by Einstein's theory of general relativity. It was as though the hidden mass of the cluster were casting a shadow on the canvas of the sky, not a shadow of darkness, but a shadow of distortion in the light from galaxies far behind. This phenomenon, known as gravitational lensing, would become a powerful tool to map the otherwise invisible. Gravity itself would unveil the dark scaffolding of the universe by the way it bends and warps light on its journey to us. Light, which normally travels in straight lines, can be compelled to take a detour in the presence of gravity. Imagine a distant galaxy shining far behind a massive cluster of galaxies. As the galaxy's light passes by the cluster on its journey to us, it encounters the cluster's gravity, and its path bends ever so slightly. By the time that light reaches Earth and is captured by a telescope, the distant galaxy's image may appear stretched, warped, or even duplicated in curious ways. In the still darkness of space, an invisible mass has left its fingerprint on a beam of light, revealing itself through a cosmic illusion. This phenomenon is known as gravitational lensing. Much like a glass lens can bend and focus rays of light, a massive object's gravity warps the fabric of space itself, curving the path of light that travels through it. More than a century ago, this effect was first confirmed on a small scale when starlight passing near our sun was observed to bend during a solar eclipse. In the vast expanses of the universe, the same principle plays out on grand scales. Entire galaxies and clusters act as lenses, distorting the light of objects lurking far behind them. The result can be breathtaking. A single background galaxy might appear multiple times, arranged around a foreground cluster in an arc, or even a complete ring of light. These ethereal rings and arcs, often tinted a faint blue in telescope images, are telltale signs of gravity's influence on light, and by extension, the presence of mass that might otherwise remain hidden. One famous example occurs when a massive galaxy cluster produces what is called an Einstein ring, a nearly perfect circle of light formed from a background galaxy's image. Such a ring appears when the distant galaxy, the intervening cluster, and our viewpoint are all almost perfectly aligned. More commonly, we see partial arcs or stretched smudges around the edges of clusters. To the casual eye, these arcs might seem like oddly shaped galaxies, but they are actually mirages, distorted images of normal galaxies whose light has been bent. Every such distortion is a message carried in light, telling us about the gravity it encountered. By carefully decoding these messages, astronomers can map out how mass, both visible and invisible, is distributed in the lensing object. In many cases, the visible matter in a lensing cluster or galaxy cannot by itself account for the extent of the light's distortion. For instance, we can calculate how much lensing effect a cluster's known galaxies and gas should produce. The actual observed lensing is often far stronger, indicating a surplus of gravity due to unseen mass. By adjusting their models to match the arcs and rings in the images, scientists effectively weigh the cluster's dark matter. They find that the majority of the lensing power comes from the invisible mass enveloping and permeating the cluster. In composite photographs of such clusters, astronomers sometimes overlay a hazy blue hue to indicate where the dark matter must lie, in great clumps around the cluster's galaxies and in an extended halo wrapping the entire cluster. The shapes and positions of the gravitationally lensed arcs simply cannot be explained without this dark matter. Light itself, bent and twisted, sketches out a rough portrait of the invisible. Gravitational lensing doesn't occur only on the scale of massive clusters. Even individual galaxies can act as lenses if a bright object lies directly behind them. Distant quasars, the brilliant cores of young galaxies, have been seen to appear as multiple points of light arranged in symmetric patterns, where a single quasar's light is split into 2 or 4 images by the gravity of a foreground galaxy. In these cases, once again, the mass needed to create the observed lensing exceeds what we can visibly detect in the lensing galaxy. The stars and gas alone would not be enough to bend the quasar's light so dramatically. But if we include a dark matter halo around the galaxy, the observations make sense. These cosmic coincidences, where nature provides just the right alignment to produce such optical tricks, offer striking evidence that an unseen mass is present and influencing light across great distances. Using gravitational lensing as a tool, astronomers have been able to create detailed maps of invisible matter. By analyzing many lensed images and working backwards through the equations of gravity, they can infer where the unseen mass must be located to cause those distortions. A remarkable picture emerges. Dark matter is not spread uniformly, but gathered into structures. It clumps around galaxies and clusters, forming the scaffolds that hold those systems together, just as rotation curves and cluster observations suggested. In one striking case, astronomers even detected a ring-like structure of dark matter in a colliding cluster, possibly left behind by a past cosmic collision. This dark ring was visible only through its lensing effect, a subtle pattern in the way background galaxies were distorted. Yet it provided direct evidence that we can observe dark matter's footprint in detail. Not all gravitational lensing is dramatic and obvious. There is also a gentler, more widespread form called weak lensing. Here, the effect on each background galaxy is tiny, perhaps a slight stretching or shearing of its image by 1% or 2, far too little to notice in one galaxy alone. But by observing millions of distant galaxies, astronomers can detect a coherent pattern, a very slight, systematic distortion of galaxy shapes, oriented around massive structures in the foreground. It's as if the entire sky is imprinted with faint fingerprints of dark matter. Each individual mark is imperceptible, but taken together, they reveal the contours of enormous, unseen masses. By statistically analyzing these subtle shape distortions, scientists build expansive maps of dark matter, tracing the invisible cosmic web that spans the universe. These weak lensing maps have confirmed what earlier clues had been whispering. On the largest scales, dark matter forms a vast, interconnected network, a cosmic web of filaments and nodes, and galaxies lie along these filaments like sparkling beads. Where the lensing signal is strongest, we find clusters and superclusters of galaxies. In between, where the lensing signal drops off, are cosmic voids sparsely populated by matter. The lensing observations act like lanterns in the dark, illuminating where mass is concentrated across space. Through them, the once theoretical scaffolding of dark matter becomes visible by its gravitational outline. We see that galaxies and clusters truly trace a grand design laid out by dark matter's gravity. By letting gravity serve as a giant cosmic lens, humanity has found a way to visualize the invisible. The distorted light from distant galaxies provides an exquisite, indirect view of what otherwise cannot be seen. It is as though dark matter itself, while remaining unseen, casts a kind of shadow through the light it bends. A shadow not of darkness, but of altered images projected on the sky. Through gravitational lensing, we have begun to perceive the immense, hidden structures that undergird the cosmos. And as these maps come into focus, they naturally lead us to consider the form of that structure itself, the vast network of matter that we call the cosmic web, the next stage of our journey through the unseen cosmos. We now step back to behold the universe on its grandest scales. Galaxies are not scattered randomly through space. Instead, they gather along vast, wispy filaments, with immense voids yawning between them. These filaments, along with nodes of clusters at their intersections, form an immense interconnected arrangement known as the cosmic web, stretching across hundreds of millions of light years. This web is the large-scale pattern of matter in the universe. In this lattice of matter, galaxies are strung like beads on nearly invisible threads, and where the threads intersect, great clusters of galaxies bloom, the dense hubs of the web. Drifting in our imagination far above this cosmic web, we would see that most galaxies reside on these faint highways of matter. The huge voids between, vast regions nearly empty of galaxies, make the filaments stand out in relief, like the veins of a leaf against open sky. Along the filaments, countless galaxies quietly line up, and between them flows a tenuous river of intergalactic gas. Over cosmic timescales, this gas streams along the filaments, feeding into galaxies and helping them grow. It is along these routes that galaxies themselves can migrate, gradually drawn by gravity toward the web's junctions. At those intersections, filaments deliver galaxies and fresh material into massive clusters, much like roads funneling travelers into a busy city center. Thus, the cosmic web is not a static structure, but a living network guiding the motion and growth of everything within it. What shapes this colossal web? The delicate filigree of the cosmic web was woven by gravity, and gravity's master architect on these scales is dark matter. In the early universe, dark matter began to clump and draw in ordinary matter, tracing out the first faint patterns of what would later become the web. Because dark matter does not emit or absorb light, the growing web was initially invisible, a ghostly framework. But as eons passed, gas fell into the same patterns under dark matter's gravitational guidance. Gradually, that gas cooled and condensed into stars and galaxies along the densest threads. The result is that today we indirectly perceive the cosmic web. We see galaxies, groups, and clusters outlining where the invisible dark matter accumulated. The luminous universe is like dew collected on a spider's web at dawn, revealing the shape of a web that was there all along. Observations have confirmed this grand design. When astronomers map the positions of millions of galaxies, they unveil immense filaments and walls separated by huge voids. Structures once thought isolated, a cluster here, a group there, are recognized as pieces of a larger weave of matter. Computer simulations, using the physics of gravity and dark matter, produce strikingly similar patterns, a cosmic web nearly identical to the one observed. This agreement between theory and observation tells us that our understanding is on the right track. Dark matter, slowly drawing itself and ordinary matter together, built the scaffolding of the universe. The sheer scale and beauty of the cosmic web inspire a quiet awe. Imagine floating at a vantage point where an entire filament is spread before you, millions of light years long. You might see a faint glow from diffuse gas, or the light of innumerable distant galaxies strung along the strand. This structure is almost incomprehensibly large, yet gossamer in form, a tenuous cosmic silk stretching through space. And though it appears nearly empty, it is the framework that dictates where galaxies form and congregate. It is the reason our Milky Way belongs to a local group of galaxies, which in turn sits on the outskirts of a filament leading toward the Virgo cluster and beyond. At the intersections of filaments, where multiple strands converge, lie the great clusters we encountered earlier. Here, the web is knotted into enormous concentrations of mass, rich in galaxies and saturated with dark matter. Filaments continuously funnel new material into these clusters, allowing them to grow over time. In these nodal regions, gravity's pull is intense, drawing in any stray galaxy that ventures near. Conversely, within the emptiness of the voids, galaxies are few and far between, marooned in vast darkness, with little gravitational attraction to pull them together. This patchwork of dense nodes, connecting filaments and lonely voids, is the grand tapestry that dark matter's gravity has woven. Recognizing the cosmic web helps us appreciate how interconnected the universe truly is. Every galaxy's story is influenced by the filament on which it lives and by the nearest cluster tugging on it. Even our own galaxy is not isolated. The Milky Way is part of this web, likely situated on a minor filament bridging larger structures. Through this network, dark matter's influence extends across unimaginable distances, organizing matter on scales far beyond any single galaxy. Now, having surveyed the vast threads of the cosmic web, we can zoom back into the scale of individual galaxies. We know galaxies gather along the web's filaments, but each galaxy also carries an invisible entourage. Wrapped around every galaxy is its own halo of dark matter, a cocoon of gravity that provides the immediate environment in which that galaxy lives and evolves. These dark matter halos are the building blocks of the cosmic web on smaller scales, and within them, galaxies find their homes. To truly understand how galaxies form and thrive, we must delve into these mysterious halos, the homes that dark matter creates for galaxies, quietly guiding their growth from within. Every galaxy, from the humblest dwarf to the grandest spiral, is cradled within an invisible halo of dark matter. This halo envelops the galaxy like a vast cocoon, extending well beyond the farthest stars we can see. If we could somehow light up the dark matter around a galaxy, we would behold an enormous, diffuse sphere surrounding the bright disk or body of stars, a sphere of influence reaching deep into the cosmic night. In our own Milky Way, for instance, the dark matter halo is thought to stretch hundreds of thousands of light years from the center, far past the edge of the visible starry disk. Though we see the Milky Way as a shining river of stars, that luminous structure is embedded in a halo containing much more mass than all those stars combined. The galaxy's bright arms and glowing core are only the tip of a much larger iceberg of matter. These halos are the homes where galaxies take shape. In the early universe, it was within clumps of dark matter that primordial gas was drawn in and began forming the first stars. The gravity of the dark halo acts as a nurturing container, gathering the raw material for a galaxy. Over time, as gas sinks to the halo's center and cools, stars ignite and a new galaxy comes to life. The dark matter, though invisible, serves as the scaffolding supporting this entire process. It provides the deep gravitational well that holds the budding galaxy together, guiding its growth by continuously pulling in fresh gas and even smaller satellite galaxies. Without the encompassing pull of a massive halo, a young galaxy's gas might drift away and its stars would scatter. The halo's gravity keeps the galaxy intact and allows it to evolve and persist. In a mature galaxy, like our Milky Way, the dark halo continues to play a quiet but crucial role. It keeps stars bound in their orbits. As we saw, those rapid stars in the outskirts owe their loyalty to the halo's gravity. The halo also acts as a kind of protective buffer, cushioning the galaxy during close encounters. When galaxies pass near each other, or even collide, their visible stars might only mingle or react during the final moments. But their halos begin to interact well before the galaxies proper meet. A galaxy's halo can tug on passing objects, stripping gas from a neighbor, or capturing small companions. Indeed, our Milky Way's halo is home to dozens of dwarf satellite galaxies orbiting within it, remnants of past interactions and mergers. In this way, halos enable galaxies to grow over time, quietly accreting mass from their surroundings and from the cannibalism of smaller systems that venture too close. Dark matter, halos also help explain why galaxies of similar type share certain characteristics. For example, the size and rotation speed of a spiral galaxy are closely tied to the mass of its dark halo. A massive halo can support a larger, faster rotating disk of stars and gas, whereas a smaller halo cannot. In elliptical galaxies, which often form through the mergers of other galaxies, the final shape and extent of the light distribution reflect not just the merging of stars, but the merging of halos. When two galaxies collide and their halos combine, the new, larger halo serves as the gravitational container for the merged system. Thus, at every turn, a galaxy's fate and properties are intertwined with the behavior of its dark matter halo. In the darkness beyond a galaxy's visible edge, the halo is not entirely smooth. Theoretical models predict that halos should be peppered with smaller clumps of dark matter, subhalos, orbiting within them. Many of those subhalos are thought to host dwarf galaxies, the tiny satellites that accompany bigger galaxies. We see hints of this in reality. Our Milky Way, for instance, is orbited by numerous dwarf galaxies and globular clusters, some arranged in patterns that suggest they trace the strands of dark substructure within the halo. It's as if the halo is a vast forest, and the dwarf companions are like little creatures or shrubs within it, each corresponding to a knot of dark matter in the larger halo's expanse. The concept of dark matter halos has become a cornerstone of modern cosmology. We now realize that galaxies are not isolated island universes, but rather the luminous centers of much larger, invisible edifices. The glittering stars, glowing nebulae, and swirling gas that we observe directly make up only a small fraction of a galaxy's true mass and extent. Enshrouding each one is an enormous halo of dark matter that binds it together and provides the gravitational stage on which its drama unfolds. It's a humbling perspective. When we peer at a majestic spiral galaxy through a telescope, we are only seeing the bright frosting atop an unimaginably large cake of dark matter. We have followed the trail of dark matter evidence from the swift orbits of stars in galaxy outskirts, to the bustling cores of galaxy clusters, to the bending of distant light, the weaving of the cosmic web, and finally down into the quiet halos embracing each galaxy. We can map these halos, simulate their growth, and observe their effects. Yet we still confront a fundamental mystery. What is dark matter made of? So far, we have described it by what it does, not by what it truly is. To complete the picture, we must shift our gaze from the cosmic structures it forms to the microscopic world of particles that might constitute it. And so, our journey turns inward, from the grand scale of clusters and galaxies to the subatomic realm, in search of the elusive particles that could be the very essence of the dark matter. All the evidence we've gathered tells us dark matter is real and abundant, yet it remains frustratingly intangible. It neither emits light nor blocks it. It slips through ordinary matter, almost as if it weren't there. What could this enigmatic substance be? One clue lies in what it is not. Over the years, scientists have ruled out nearly all forms of familiar matter as the source of the missing mass. It is not made of stars, not even the faintest dwarfs or burnt-out cinders, for there simply aren't enough of them hiding unseen to account for the vast gravity we detect. It is not great clouds of cold gas, for such clouds would reveal themselves through absorption or emission of radio waves and light. Could it be black holes? Perhaps countless primordial black holes, sprinkled throughout the universe? Some have speculated that tiny black holes born in the Big Bang might populate the cosmos, each contributing a bit of hidden mass. But careful searches for their gravitational effects like the slight magnification of background stars as black holes drift in front of them, indicate they cannot make up more than a small fraction of the dark matter. The conclusion grows increasingly firm. The bulk of dark matter must be something truly different, something beyond the ordinary roster of protons, neutrons, electrons, planets, and stars. The leading idea is that dark matter consists of a new kind of elementary particle, or family of particles, that pervades the universe. Unlike the known particles that make up the atoms in our bodies and in stars, these dark matter particles would interact with light and with ordinary matter only very weakly, if at all. In effect, they are invisible and ghostly, making themselves known solely through gravity. Physicists have a name for one popular class of dark matter particle, the WIMP, short for weakly interacting massive particle. The name paints an evocative picture. A massive particle, meaning it has heft, possibly comparable to dozens or hundreds of protons, that interacts so feebly that it can pass through normal matter as a whisper passes through a wall. If WIMPs exist, then right now, this very second, trillions of them could be streaming through your body undetected. They would sail through the Earth as though it were mostly empty space, which, on the subatomic scale, it largely is. We would never know, except that collectively their gravity shapes galaxies and holds clusters together. For a long time, WIMPs were the favoured dark matter candidate. They fit neatly into certain theoretical frameworks of particle physics that extend our current standard model. What's more, if WIMPs had been born in the hot aftermath of the Big Bang, calculations showed that just the right number might remain today to account for dark matter, a coincidence dubbed the WIMP miracle. Buoyed by this idea, scientists embarked on ambitious experiments to actually catch these particles in the act. They built large detectors in deep underground laboratories, beneath mountains or in old mines, to shield them from cosmic rays and other false signals. These detectors, often vats of ultra-pure liquid xenon, or crystals chilled to near absolute zero, sit in silence, waiting for the most elusive collision in the universe, a dark matter particle gently bumping into an atomic nucleus inside the detector. The hope is that, very occasionally, a WIMP will smack into an atom and give it a tiny kick, producing a faint flash of light or a slight heat pulse that we can measure. Decades of effort have pushed these experiments to ever greater sensitivity. Once a year, once a month, then perhaps once a century, the expected interaction rates became that small. So far, none of these detectors has yielded a definitive dark matter sighting. The WIMPs, if they are out there, remain in hiding. This lack of detection has been sobering, forcing scientists to reconsider some earlier assumptions and widen the search. Meanwhile, other ideas for dark matter's identity have been gaining ground. One intriguing possibility is an ultralight particle called the axion. Axions would be extremely low in mass, perhaps a trillionth or even a quintillionth the mass of an electron. And they interact with ordinary matter so subtly that they have so far evaded detection. Originally proposed to solve a puzzling problem in quantum physics, axions, if they exist, could be plentiful enough to make up dark matter. Rather than behaving like individual particles, an enormous number of axions would form something akin to a pervasive field, like a barely detectable background hum permeating all of space. To hunt for axions, scientists use sensitive radio receivers and strong magnetic fields, listening for a faint, telltale signal that axions might generate as they convert into photons under the right conditions. These experiments, too, demand exquisite care. They've been compared to trying to hear a whisper in the middle of a thunderstorm. As of now, axions remain hypothetical, but the search is intensifying with each passing year. Beyond WIMPs and axions, there is an entire zoo of other hypothetical dark matter candidates. Some researchers wonder if sterile neutrinos, a heavier, inert cousin of the normal neutrinos that trillions of which zip through us each second, might be the answer. Others speculate about exotic states of matter, like dark particles that interact via their own hidden forces, forming dark atoms and dark galaxies that mirror our own in structure, but not in substance. There are even far-out ideas involving extra-spatial dimensions or modifications of gravity at large scales as alternatives to the particle dark matter hypothesis. At present, none of these ideas has more than circumstantial support. The truth is, until we either detect the dark matter particle directly or create it in a particle accelerator, its true nature will remain elusive. It might turn out to be something we predicted, or it might surprise us entirely. Despite the mystery, the quest to identify dark matter is one of the most profound scientific adventures of our time. With each failed detection, we learn a little more, narrowing down the possibilities and refining our theories. An absence of evidence is not wasted effort. It guides us, telling us where not to look and pushing us toward new ideas. At the same time, technology marches on. The detectors we have now are orders of magnitude more sensitive than those of a decade ago. Particle accelerators like the Large Hadron Collider continue to smash protons together at fantastic energies, looking for any hint of new particles that could be related to dark matter, such as missing energy that would imply an unseen particle carried it away. Space-based observatories keep watch for peculiar excesses of high-energy particles or gamma rays that might arise from dark matter particles, annihilating each other in the depths of space. So far, these searches have been inconclusive, but they add pieces to the puzzle, constraining what dark matter could be and how it behaves. There is also a poetic side to this scientific detective story. We find ourselves immersed in an invisible ocean of dark matter, orbiting the center of the Milky Way, along with the sun and planets, like fish unaware of the water around them. Every moment, billions upon billions of dark matter particles, if they are particles, stream through us and through the Earth without a trace. We are, quite literally, swimming in a sea of the unknown. To sense it, we have had to become extraordinarily clever and patient, eavesdropping on the cosmos with devices so quiet and sensitive that they can hear the lightest tap from a particle that hardly ever taps at all. Deep underground in vaults of silence, scientists keep vigil for a single flash that would announce a dark matter particle has appeared. High in mountain observatories, they scan the heavens for subtle clues in starlight and cosmic rays. In these pursuits, there is a sense of communion with the cosmos, an attempt to listen to the universe's whispers after comprehending some of its shouts. Even as we sift the silence, the nature of dark matter remains one of the deepest unsolved problems in science. Will it be a WIMP, revealing itself at last in the next generation of detectors? Will an axion tune in as a faint tone in a carefully prepared cavity experiment? Or will it be something utterly unexpected, a new facet of physics that forces us to rethink what we know? For now, the answer remains hidden in the dark. Yet we do not lose hope. We have the roadmap drawn by cosmic observations, and we have the tools of experimentation and theory to guide us. With each passing year, we close in a little more on this elusive secret. We have journeyed through a rich landscape of evidence and conjecture about dark matter, but nature sometimes offers us a more visceral demonstration of a phenomenon, a cosmic experiment that separates the invisible from the visible in a way that we can plainly see. Such is the case with colossal collisions in space, when whole galaxies and clusters of galaxies crash into each other. In these rare cosmic smash-ups, dark matter and normal matter part ways, allowing us to observe their separation and truly grasp that one is not the other. Our next step takes us into the aftermath of these cosmic collisions, where we witness how the unseen mass stands apart from the glowing matter, revealing itself in the most dramatic fashion. Occasionally, the universe provides a natural experiment on a colossal scale. Imagine two immense clusters of galaxies hurtling into one another after eons of approach. When they collide, it is not a sudden, fiery crash like cars on a highway. Rather, it's more like two clouds of insects passing through each other. The individual galaxies, each separated by vast gulfs of space, simply glide by, hardly ever striking one another directly. But the clusters are filled with something else, a hot, tenuous atmosphere of gas, an invisible, to our eyes, but crucial component of their mass. When the clusters collide, this gas does interact. It crashes together, slows down, and heats up, glowing brightly in X-ray light. In one well-studied cosmic collision, a smaller cluster plunged through a larger one, and its gas was stripped off in the impact, left trailing behind like a shimmering cloud. Astronomers nicknamed this system the bullet cluster, because in X-ray images the gas streak resembles a bullet's path through the air. Now consider what happens to the dark matter in this event. Dark matter, being collisionless, doesn't slow down when the clusters collide. It doesn't clump up or stick, it just sails through. In the bullet cluster, as the two clusters crossed, their dark matter halos moved ahead of the wreckage of gas and kept going. The galaxies, which contribute only a small fraction of the mass, mostly rode along with the dark matter. The result was startling. After the collision, the main mass of each cluster ended up separated from the bulk of its ordinary matter. How can we tell? By mapping the gravity through gravitational lensing. Astronomers trained their telescopes on distant galaxies whose light passed through the bullet cluster region, and they observed how that light was bent. They found two dominant lensing clumps of mass, indicated by a blue shading in the reconstructed images, that were now ahead of the X-ray bright gas clouds, shown in pink. These clumps correspond to the dark matter of the two clusters, which had simply passed through each other. The ordinary matter, the hot gas, however, had slammed together and remained behind, near the center. In plain terms, the light told us that most of the mass, dark matter, was no longer where most of the ordinary matter was. This observation was a watershed moment. Here was a direct visualization of dark matter's presence and behavior. In the bullet cluster, we effectively see two entities: the glowing gas that collided and stopped, and the dark matter that didn't even feel the collision and sped on. It's hard to imagine a clearer demonstration that dark matter is something separate from normal matter. If what we were calling dark matter was really just some unconventional property of gravity tied to ordinary matter, we wouldn't expect the mass to separate from the matter we see. But it did. The bullet cluster, therefore, stands as a striking confirmation. An invisible mass, immune to collision forces, carries most of the cluster's gravity with it. This cosmic encounter also allowed scientists to probe the dark matter particles' nature. The fact that the dark matter halos went through each other without obvious disruption tells us that dark matter interacts very little, even with itself. If dark matter particles did collide or drag against each other in such events, the dark matter might have slowed down or become offset in more complex ways. Instead, the dark matter clumps are intact and ahead of the gas, implying that the dark particles pass through one another like ghosts. This puts limits on how much dark matter particles can bump or stick to each other. In technical terms, it sets an upper bound on their self-interaction cross-section. So far, they appear to be extremely polite, hardly interacting at all except via gravity. The bullet cluster is not unique. A handful of other cluster collisions have been studied, and though each system has its own geometry and story, the general outcome is similar. The center of mass, deduced from gravitational lensing, ends up displaced from the center of visible matter, deduced from X-rays of gas or the galaxy's distribution. In some cases, like the train wreck cluster Abel 520, there have been puzzling details. For instance, reports of a dark mass concentration with few galaxies. But overall, the simplest explanation across these observations is that dark matter exists and behaves as a collisionless component. Each new collision we observe is like watching the same play performed with different actors on a different stage, but the plot remains the same. In these cosmic pile-ups, normal matter slows and separates, while dark matter blithely continues on its way. From these violent events, we gain confidence that our understanding of an unseen mass is not an illusion of our methods. It's really out there. Seeing is believing. And in a sense, we have seen dark matter in the bullet cluster and its kin, not by its light, but by its distinct behavior and gravitational imprint. It solidifies the idea that dark matter is an independent ingredient of the universe, with its own existence apart from gas, stars, and dust. Still, not every insight about dark matter comes from such dramatic episodes. Much of what we have learned has come from patiently mapping the universe in large surveys, looking for subtle patterns rather than sudden collisions. We turn now to those broad and gentle approaches, the grand inventories of galaxies and the statistical fingerprints, which have acted as lanterns, guiding us through the dark. Having witnessed dark matter's impact in the heat of cosmic collisions, we will now survey the calmer cosmos, using flows of galaxies and patterns in their distribution to chart the unseen and deepen our understanding of this dark scaffolding that underlies the visible universe. In addition to dramatic one-time events, astronomers have developed more subtle ways to illuminate the dark matter landscape. One approach is to survey the universe on the grandest scales, mapping where galaxies are and how they move. By observing the motions of thousands of galaxies, scientists can detect the gravitational pull of things unseen. For example, our own Milky Way and its neighbours are not simply drifting randomly. They are part of a larger flow. We and other galaxies in our vicinity are moving toward a particular patch of sky in the southern hemisphere, as if drawn by an immense gravity there. This mysterious region has been dubbed the Great Attractor. It lies about 200 million light-years away, in the direction of the constellation Centaurus, partly hidden behind the Milky Way's foreground stars and dust. We cannot clearly see what's at that location, because our own galaxy's disk obscures much of it. But the motions of galaxies in our neighborhood, all streaming slightly in that direction, suggest a huge concentration of mass. Many galaxies, perhaps a massive cluster or supercluster, reside there. Crucially, the gravity needed to cause these motions is far more than what's visible. The Great Attractor's pull hints at a titanic amount of dark matter in that region, pulling on galaxies over tens of millions of light-years, like a giant, unseen magnet. This use of galaxy flows, measuring how galaxies deviate from the smooth expansion of the universe, is one way to map invisible mass. In our local universe, for instance, galaxies are not expanding perfectly uniformly away from each other. There are small deviations. Our local group of galaxies is falling toward the Virgo cluster, a massive cluster about 50 million light-years away, at a few hundred kilometers per second. That motion tells us Virgo has a lot of mass, mostly dark. On a larger scale, groups and clusters themselves exhibit flows toward even larger concentrations, like the Great Attractor and beyond, such as the Shapley supercluster, which is thought to be the most massive structure in our extended neighborhood. By compiling these motions, like a cosmic current map, astronomers create a gravitational map of where mass, visible or not, resides. These studies indicate a universe in which matter, especially dark matter, is clumped into filaments and overdensities, and galaxies respond by drifting along gravitational valleys towards the deepest pits of gravity. Another approach is simply counting and mapping where galaxies and galaxy clusters are, and examining the statistical patterns in this cosmic distribution. Imagine dividing the sky into patches and counting galaxies, or measuring how likely galaxies are to be a certain distance apart. These analyses reveal that on large scales, the universe has a very definite pattern. Galaxies are clustered and not randomly scattered. There's a subtle preferred separation scale of about 500 million light-years, a footprint of sound waves ringing through the early universe, now imprinted as the baryon acoustic oscillation (BAO) feature in the clustering of galaxies. Detecting this faint ripple in galaxy positions was a triumph of surveys like the Sloan Digital Sky Survey. And why does this matter for dark matter? Because the existence and size of that ripple and the overall clustering strength at various scales depend on the amount of dark matter. Theoretical models of structure formation, when run with different dark matter content, produce different clustering statistics. The observations best match a model where about 85% of the matter is dark. If there were no dark matter, or significantly less, the galaxies would be distributed differently today. The BAO peak would have a different prominence. Small-scale clustering would be weaker, since normal gas pressure would have prevented too much clumping early on. And overall, there would be fewer large structures. The fact that our observed universe matches the dark matter-rich simulations is a strong, albeit indirect, confirmation that our picture is on the right path. Counting galaxy clusters is another statistical lantern. Clusters are rare beasts. The fact that we see any at all is informative. The number of galaxy clusters of different masses and at different epochs in cosmic history is very sensitive to the cosmic recipe. If dark matter were less abundant, clusters would take longer to form, and we would see fewer of them, especially in the early universe. Surveys that find clusters by their X-ray emission or by their subtle distortion of the cosmic microwave background's light through the Sunyaev-Zeldovich effect have measured cluster populations over time. These measurements align well with a universe dominated by cold, dark matter. In fact, they help refine how much matter, dark plus normal, the universe contains. The answer that comes back is consistently around 30% of the critical density, the density needed to halt expansion in a no-dark energy universe, with the remainder presumably in the form of dark energy. Out of that 30% matter, only 1/5 is normal. The rest must be dark. Such findings show up again and again in different guises. It's like hearing the same answer spoken in different languages by the cosmos. Then there's the cosmic velocity field, a cousin to the flows we described, but measured in a statistical way across large volumes. Galaxies carry a memory of the gravitational forces they've experienced in their peculiar velocities, deviations from the pure Hubble expansion. By mapping these peculiar velocities in different regions, scientists can reconstruct the underlying matter density fluctuations through a relation, known in cosmology as the velocity-density relation. This has been done for relatively nearby galaxies, producing maps of our local supercluster's matter distribution, which confirm that known structures like Virgo, Great Attractor, Shapley, etc., are gravitating masses influencing motions. More interestingly, on larger scales, peculiar velocity studies imply a certain amplitude of matter clumping. They suggest that there is a lot of gravitating matter that is not seen directly, again consistent with roughly 5 times more dark matter than visible. All these methods, peculiar flows, clustering counts, cluster surveys, cosmic shear from lensing, which we discussed earlier in detail, interlock like pieces of a grand puzzle. When assembled, they give us a consistent cosmological model, one in which dark matter is a major player. We can even put numbers on it. The best current measurements indicate that about 27% of the universe's total energy mass content is in matter, and of that fraction, about 5% is normal matter and 22% is dark matter. The remaining roughly 68% is in the form of dark energy, which we have yet to explore, but soon will. In other words, dark matter accounts for roughly a quarter of everything, and about 85% of all matter. This concordance has been a remarkable success story of modern cosmology. Multiple lines of evidence, from the cosmic microwave background to galaxy surveys, all pointing to the same basic inventory for the universe. Equipped with these detailed maps and measurements of the unseen, we can now venture to ask, how did this dark scaffolding come to be in the first place? For that, we must turn our gaze back to the very beginning of structure, to the primordial fluctuations in the early universe that gave rise to the cosmic web we see today. Clues to that origin lie in the oldest light in the universe, the cosmic microwave background, and in our theories of the universe's birth. By examining the infant universe, when the first light was set free and the first seeds of structure were planted, we can connect the dots from those simple beginnings to the richly structured cosmos of the present day. Our journey now pivots from observing what is to uncovering how it all began, as we seek to understand how dark matter's blueprint was drawn in the dawn of time, and how that blueprint guided the emergence of the first stars and galaxies. To truly grasp how dark matter shaped the cosmos, we must travel back to the very beginning, to the era of the universe's first light. This first light is not the light of the first stars, but something even older, the cosmic microwave background, the faint afterglow of the hot Big Bang. When the universe was an infant, about 380,000 years old, it was filled with a brilliant, blazing plasma of particles and radiation. Space was like the interior of a star, opaque and glowing, and any light was quickly scattered by electrons. As the universe expanded and cooled, there came a moment when protons and electrons combined to form neutral hydrogen atoms. Suddenly, the fog cleared. The cosmos became transparent. Light that had been trapped now streamed freely in all directions. That light is the cosmic microwave background, CMB, and we observe it today as a cool, faint microwave glow coming from every patch of sky, literally the oldest light we can see. The CMB isn't perfectly uniform. Across the sky, it has tiny variations in temperature, only about 1 part in 100,000 above or below the average. These slight irregularities are a cosmic blueprint. They show us the seeds of structure, the tiny density ripples in the early universe that would later grow into galaxies and clusters under the force of gravity. By studying these patterns with exquisite precision, as missions like Planck and WMAP have done, cosmologists can infer the cosmic ingredients at that early time. The results are striking. They tell us that ordinary matter, the stuff that makes atoms, stars, and us, was only a minor component, while dark matter was already dominant in terms of mass. The evidence is encoded in the size and relative heights of the slight hot and cold spot patterns. In particular, the imprint of dark matter's gravity can be seen in the way it influenced the oscillations, sound waves, in the primordial plasma. Without diving into the technical details, one key takeaway is that the CMB data indicate a universe composition of roughly 5% normal matter, 25% dark matter, even back then. These ratios are the same that we infer today, showing that dark matter was already quietly doing its job, providing extra gravity in those early times. Dark matter's role in the infant universe was crucial. In that early plasma, photons, light, and baryons, protons and neutrons, were tightly coupled. As light pushed outwards, it resisted gravity's pull on the normal matter. Dark matter, however, felt gravity, but not the pressure of photons. It could start clumping earlier. By the time the CMB was emitted, when the universe became transparent, dark matter had already gathered into shallow potential wells. The normal matter, once free of the photon's grip, began to fall into these dark matter wells. This gave structure formation a tremendous head start. Soon the universe entered what we call the Dark Ages, a period after the CMB's release, but before the first stars ignited. During these ages, there were no stars shining yet. But in the dark, the cosmic web of dark matter was drawing filaments together and deepening the wells, and ordinary matter, now just neutral gas, was slowly accumulating in them. Fast forward a few tens to a couple of 100 million years. In the densest pockets of gas, at the centers of sizable dark matter halos, the first stars were born. These population 3 stars, as we call them, were likely very massive and short-lived, composed almost purely of hydrogen and helium, since no heavy elements existed yet. They burned brightly and lived briefly, ending in supernova explosions that enriched the surrounding gas with the first heavy elements. But their formation was enabled by dark matter. Without the dark matter, halos concentrating the gas, the universe might have taken much longer to form stars, because the gas on its own would have struggled to collapse in the face of pressure and the still relatively smooth initial conditions. With dark matter's help, however, the gas had places to collect and cool. The first starlight thus appeared perhaps as early as 100 to 200 million years after the Big Bang. As soon as stars and galaxies began to form, they in turn affected the universe around them. Their light started to ionize the neutral hydrogen in the intergalactic space, a process known as rayonization. Bubbles of ionized gas grew around each early galaxy and quasar, eventually merging and clearing out nearly all the hydrogen fog by about 1 billion years after the Big Bang. Throughout this epoch, dark matter was the skeleton on which this transformation took place. Galaxies formed preferentially in high-density dark matter regions, filaments and nodes of the cosmic web, and those are where rayonization bubbles first appeared and grew. The large-scale distribution of dark matter thus influenced where the universe became transparent again to ultraviolet light. Observations today allow us glimpses into those early times. The Hubble Space Telescope, and now especially the James Webb Space Telescope, have identified galaxies that existed when the universe was only a few 100 million years old. Remarkably, some of these galaxies are more developed and massive than we expected for that era. This could be another hint of dark matter's efficacy. If the scaffolding of dark matter was very well established early on, as our lambda CDM cosmological model suggests, it provided ample opportunity for gas to funnel in and form stars quickly, perhaps quicker than our older simplified models predicted. Thus, when we see a surprisingly massive galaxy at, say, 400 million years old, it's not inexplicable. It's a sign that structure formation was underway fast, courtesy of dark matter's guiding hand. Bringing the story full circle, we live in a universe that is 13.8 billion years old, and over that vast time, dark matter has been the silent partner in the creation of structure. Tiny quantum fluctuations from the universe's birth, possibly amplified during a brief period of hyper-rapid expansion called inflation, laid down the initial pattern. the light spots and dark spots in the CMB. Dark matter took those and, with its gravity, exaggerated them. The dense spots grew denser, the voids emptier. Normal matter followed suit once it could. Galaxies ignited, clusters coalesced, superclusters linked up, tracing the outline of dark matter's design. The galaxies we see today, the groupings they come in, even the emptiness of a big void like the Bootes void, all reflect where dark matter is or isn't. In reflecting on this cosmic history, we appreciate that without dark matter, the universe would likely be a very different place. Galaxies might have taken far longer to form, and the universe at 14 billion years might still be a more primordial, lumpy soup of gas, with perhaps only small protogalaxies, if anything. The fact that we have grand spiral galaxies and giant ellipticals and glittering clusters by this epoch is largely thanks to the gravitational scaffolding provided by dark matter. In a poetic sense, dark matter was the mold in which the cosmic structure set. Our exploration of dark matter has carried us from the present-day galaxies all the way back to the realm of the first light and the first stars. We have illuminated many aspects of this dark scaffold: how it influences galaxy rotations, binds clusters, warps light, weaves the cosmic web, and accelerates the emergence of structure after the Big Bang. We have also confronted the mystery of its true nature and seen the lengths to which scientists go to uncover it. And yet, as comprehensive as this journey has been, it is still not the end of the story of unseen forces. Surprisingly, the majority of the universe, even more than dark matter, is composed of something even more mysterious. In the late 1990s, astronomers discovered that the expansion of the universe is speeding up, driven by what has been termed dark energy. If dark matter is the invisible scaffold pulling things together, dark energy is the invisible phenomenon pushing the fabric of space apart. It does not clump in halos or form webs. It seems to be a property of space itself, operating uniformly everywhere, and it currently dominates the dynamics of the cosmos. As we conclude this part of our cosmic journey, we stand at a threshold. We have come to understand the role of dark matter, the shadow skeleton of the cosmos, from the galaxies around us to the very first light of the universe. Now our gaze turns to an even more elusive influence, one that will determine the fate of the universe on the largest scales. With the same sense of wonder and determination, we will turn toward this dark energy, exploring how it was discovered, what it might be, and how it shapes the destiny of everything. In the next chapter of our exploration of the unseen cosmos, we shift from the darkness that binds the universe together to the darkness that thrusts it apart, carrying forward our quest to illuminate the hidden forces that shape the universe. Space itself drifts outward, carrying galaxies with it. Across unimaginable distances, galaxies quietly slip away from each other as the universe gently expands. The light they shine towards us is stretched en route, its once bluer waves drawn into longer, redder hues by this cosmic expansion. In this way, distance is written in color. The more space has stretched during a photon's journey, the more its color skews toward red. Nearly a century ago, astronomers noticed this subtle reddening of distant galaxies' light and realized what it meant. In 1929, Edwin Hubble observed that almost every galaxy is receding from us, and that farther galaxies recede faster. This was a stunning revelation. It implied that space itself is expanding in all directions. Galaxies are not flying apart through static space like cosmic debris. Instead, the very fabric of space between them is steadily growing. To picture it, imagine raisin dots on a ball of dough as it rises. As the dough expands, each raisin moves away from the others without having to travel on its own. In our universe, we sit on one raisin, our galaxy, and see all others drifting away. There is no special center to this expansion. Every point observes the same outward drift. If we lived in a distant galaxy, we would likewise see our Milky Way's light shifted to red, and conclude it too is moving away. The expansion is everywhere and everywhen, a smooth and gentle stretching of all distances. This expansion quietly governs the large-scale fate of the cosmos. Over billions of years, it has pulled galaxies apart into a vast cosmic web, diluting matter and cooling the once fiery universe. It also provides a kind of clock. By measuring the degree of redshift in distant galaxies, astronomers can infer how long light has been traveling, and thus how much the universe has grown in that time. The relationship, known as Hubble's law, links a galaxy's distance with how fast it's receding. By this law, a galaxy twice as distant moves away twice as fast, carried by space's expansion. Yet the motion is gentle on human scales. Galaxies themselves remain bound internally by gravity. It's the space between galaxy clusters that swells over eons. If we could watch in fast forward, we'd see the tapestry of galaxies slowly drifting apart, the darkness between them widening. The telltale signature of this drift is the redshift, a cosmic Doppler effect, not from movement through space, but from the expansion of space itself, stretching out each wave of light. Like the lowering pitch of a siren receding into the distance, the reddening of a galaxy's light speaks of its increasing separation from us. Over time, this discovery completely changed our understanding of the universe. It meant that the cosmos was not eternal and static, but dynamic and evolving. Extrapolating this expansion backwards, all galaxies crowd closer in the past, pointing to a time when everything was hot and dense together, the birth of the universe itself. The gentle stretch of space we observe today is the ongoing aftermath of that primal event, and in the faint background of the sky there lies a relic of that fiery beginning, a dim afterglow from the universe's infancy, stretched to microwaves and still bathing us in light. In the darkness of space, beyond the shine of all galaxies, a faint whisper of light permeates the cosmos. It comes from every direction, an almost uniform glow that remains when all stars and galaxies are removed from view. This is the cosmic microwave background, the soft afterglow of the Big Bang's initial brilliance. Once, over 13 billion years ago, the whole universe glowed white-hot. As it expanded and cooled, that searing light was left stranded, stretched into microwave wavelengths by eons of expansion. Today it appears as a very cold, faint radiation, just 2.7 degrees above absolute zero, yet it is literally everywhere, a relic of the time when the cosmos was an infant. This gentle background light was first detected in the 1960s as a persistent hiss of microwave noise coming from the sky. At first, its discoverers were puzzled. They found a glow that seemed to emanate from all of space, day and night, with no obvious source. Soon, scientists realized they had stumbled upon the oldest light in existence, a fossil light from when the universe was only a few 100,000 years old. At that young age, the universe had finally cooled enough for matter to settle into neutral atoms, allowing light to travel freely for the first time. The cosmos, once an opaque fog, turned transparent, and a burst of light was released, a flash that has been travelling ever since. We now see that flash as a feeble microwave glow, stretched by space from fiery brightness to a cool whisper. Though faint and uniform at first glance, this afterglow carries a detailed imprint of the newborn universe. Sensitive instruments, such as the Planck satellite and others, have mapped the cosmic microwave background and found it mottled with tiny colour differences, slight warmth and coolness at the level of mere millionths of a degree. These speckles in the map are the cosmic echoes of primordial ripples. In the Planck map of the sky, for example, faint blue and red patches reveal regions that were minutely cooler or hotter than the average. The cooler, blue, spots correspond to areas that had ever so slightly higher density all those eons ago. By contrast, the slightly hotter spots were less dense regions. In those denser blue patches, gravity had a little extra foothold. Over cosmic time, those tiny differences grew into big ones. The denser spots would contract further under gravity's pull, seeding the formation of clusters of galaxies and vast structures. Meanwhile, the less dense zones would become the cosmic voids, great empty regions with few galaxies. Thus, the map of the microwave background is like a baby picture of the universe, showing the faint outline of the structures to come. What's astonishing is how smooth the picture largely is. The young universe was almost uniform, varying by only 1 part in 100,000. Yet those minute ripples were enough. The cosmic microwave background, in its dim, cool glow, quietly encodes the blueprint from which all galaxies would eventually grow. Gazing at this afterglow is a bit like looking at the horizon of time. It marks the limit of how far back we can see with light. Beyond it, earlier than about 380,000 years after the Big Bang, the universe was opaque, a fiery plasma that no light could escape. So this whispering wall of light is a cosmic horizon, a curtain drawn across the very first chapter of the cosmos. On this curtain, we see the faint pattern of primordial fluctuations, preserved like ancient markings. They are the echoes from an infant sky, a gentle, sibilant background that fills the darkness, reminding us that the universe was once very young, hot, and full of light. And those subtle ripples in that infant light would soon grow into something more substantial, the seeds of stars, galaxies, and clusters that populate the universe today. The tiny fluctuations visible in the cosmic microwave background were not just random speckles. They were the fading sound of the early universe. In that primordial fireball, space was filled with a hot, dense plasma where matter and light were tightly coupled. Within this plasma, pressure and gravity were dueling forces. Gravity tried to pull matter into denser clumps, while intense heat pressure pushed back. This tug of war set off waves, literal sound waves, that rippled through the hot young cosmos. We call these primordial oscillations acoustic waves because they are analogous to sound, compressing and rarefying the plasma in enormous spheres. For the first 380,000 years, these cosmic sound waves rang out, creating subtle density waves everywhere. When the universe cooled enough and atoms formed, these sound waves abruptly froze in place. The plasma's pressure ceased to push outward, and gravity began to take over the little density enhancements that remained. The once rippling matter became still, with slightly more matter concentrated along the crests of those ancient sound waves. Over the next hundreds of millions of years, those denser regions, the ripples imprinted in the matter, served as seeds for structure. Gravity drew more gas into them, and gradually the first stars ignited within these concentrations. Stars gathered into galaxies, and galaxies drew together into clusters, often along the very lines etched by those primordial waves. Thus, the grand design of the cosmic web was influenced by sound in the infant universe. Regions where the waves had piled up matter became the first galaxies and clusters, while troughs in the waves became vast voids. Even today, billions of years later, we can detect a faint memory of those ancient ripples in the distribution of galaxies. There is a slightly preferred separation between galaxies, about 500 million light years. That reflects the imprint of those frozen sound waves. In other words, if you pick any galaxy at random, you are marginally more likely to find another galaxy around 500 million light years away than at some slightly smaller or larger distance. This is a very subtle effect, but it has been measured in large surveys of galaxies. It's as if the universe still carries an echo of its own baby cries, translated into the clustering pattern of galaxies strewn across space. Astronomers call this phenomenon baryon acoustic oscillations, the imprint of primordial sound on the baryonic normal matter distribution. These acoustic ripples act as a kind of standard ruler in cosmology, because their original size is known from physics, and we can see how the scale of that pattern has expanded over time. By measuring the spacing of galaxies today, and at various points in the past, scientists can infer how much the universe has expanded between those times. In this way, the once heard but now silent music of the early universe helps us map the expansion history of the cosmos. The important point is that from the very smooth, hot plasma of the early universe, small ripples, literally sound waves, set the stage for all the structure we see now. The galaxies, clusters, and cosmic voids of today are the grown-up result of those primordial vibrations. We are essentially living amid the aftermath of ancient sound. When we look at maps of galaxy clusters, billions of light years across, we are seeing frozen chords from the universe's infancy. Gravity did the work of amplifying the tiny notes into the grand cosmic structures, but the initial patterns were laid down as pressure waves in the first moments after the Big Bang. What was it that created those first tiny variations in density? Those seeds that allowed sound waves to exist in the first place? To find the answer, we must journey back to an even earlier epoch, a fleeting moment, right at the dawn of time, when the universe experienced a remarkable surge of growth. To uncover the origin of those initial seeds, the tiny density variations that the sound waves played upon, we must travel to a split second after the universe's birth. In that moment, the cosmos underwent a phenomenal growth spurt known as cosmic inflation. Inflation was an unimaginably rapid expansion that occurred when the universe was less than a trillionth of a second old. In an instant, space itself blew up in scale by a staggering factor, driving apart any initial irregularities and smoothing the young universe almost perfectly. It was as if the cosmos took a single enormous breath, expanding far faster than the speed of light, not because things were moving through space that fast, but because space itself was swelling. This early burst set the stage for everything that followed. During inflation, regions of space that were once microscopically close were pulled far beyond each other's horizons. In effect, inflation solved a puzzle: how the universe came to be so uniform from place to place. Distant corners of the cosmos, which would otherwise never have exchanged light or information, were originally close together before inflation pushed them apart. This explains why the cosmic microwave background looks so even. Regions on opposite sides of the sky have almost the same temperature because, long ago, they were in contact, sharing heat, before the great expansion separated them. Inflation ironed out the wrinkles of space, like pulling a crumpled sheet taut until it is smooth. Any curvature the universe might have had was flattened away, which is why today space appears geometrically flat on large scales. Yet inflation did not make the universe completely featureless. In fact, one of the miracles of this theory is that it provides the seeds of structure. During that tiny fraction of a second, while space was expanding at mind-boggling speed, quantum fluctuations, essentially random jitters on the subatomic scale, were stretched to enormous sizes. Minuscule differences in density that originated in the quantum foam were blown up to macroscopic scales. When inflation ended, these imprinted irregularities became the tiny density variations that we later observe as slight temperature spots in the cosmic microwave background. In other words, inflation planted the seeds that would grow into galaxies. The primordial sound waves we spoke of were able to propagate because these seeds, those slight over and under densities, were already present to set them in motion. The idea of inflation emerged in the 1980s as a bold extension to the Big Bang theory. It brilliantly answered several deep questions. For example, why is the universe so homogeneous? The horizon problem. Why is it so flat? The flatness problem. Inflation's rapid stretching explains both. It made everything look uniform and flat by sheer expansion. It also provided a mechanism to greatly dilute any exotic relics like magnetic monopoles that might have been created early on, thus avoiding an overabundance of such things, solving the monopole problem. Over time, observations have supported the inflationary picture. The pattern of fluctuations in the cosmic microwave background, those tiny variations in temperature, fits well with what inflation predicts. A very uniform universe with subtle, random irregularities, just of the right magnitude. Think of inflation as the universe's initial setup. A brief, spectacular blow-up that gave us a smooth, flat cosmos with just enough tiny unevenness to eventually form stars and galaxies. It's an elegant notion that all the structures we see today, from galaxies to clusters, were spawned from quantum whispers amplified by inflation to cosmic size. While we have strong evidence supporting inflation's outcomes, the exact details of how it happened remain mysterious. We don't yet know what triggered this explosive expansion. It might have been driven by a high-energy field, or something like a false vacuum state that suddenly released energy. This remains a frontier of cosmology. What we do see are its fingerprints, the uniformity of the cosmic background, the flat geometry of space, and the very existence of those primordial ripples. Inflation's legacy is the smoothness of the universe and the seeds of structure within it. Once inflation ended, the universe continued its more sedate expansion, now filled with the same almost uniform glow, and the stage was set for the next chapter. In the calm after that initial storm, the universe was incredibly hot and dense, filled with particles and radiation. In that environment, a new process began, one that would forge the first atomic nuclei out of the primordial soup of particles. As the universe expanded and cooled a bit more, it entered a brief window where light elements could form, a recipe being cooked in the first minutes of creation. After the furious tumult of inflation, the universe settled into a hot, dense state that began the conventional expansion described by the Big Bang theory. In the first seconds and minutes, conditions were extreme. Temperatures of billions of degrees, matter in an elemental form. The universe was a roiling primordial soup of fundamental particles, protons, neutrons, electrons, and photons, all mingling in a blazing plasma. As the seconds ticked by, the soup cooled just enough to allow protons and neutrons to start sticking together. This was a brief but crucial era, lasting only about 3 minutes, in which the first atomic nuclei were cooked up. It's often poetically called the first 3 minutes, during which the universe performed a kind of light element alchemy. In that short span, the basic recipe unfolded. Free neutrons combined with protons to form deuterium, a heavy isotope of hydrogen. Deuterium, essentially a proton and neutron together, was like the first building block. Once some deuterium formed, it quickly fused further. Two deuterium nuclei could merge into helium, or deuterium could fuse with another proton or neutron to make helium-3 and then helium-4. Within minutes, most free neutrons ended up bound in helium nuclei. The outcome of this brief burst of nucleosynthesis was a universe filled mostly with hydrogen, the lone protons that didn't fuse, and helium, the fused pairs of protons and neutrons, along with trace amounts of a couple of other light elements like lithium. Essentially, the cosmos's first chemical elements were born in this initial furnace, about 3/4 hydrogen and 1/4 helium by mass, with just a pinch of lithium. This process is called bigbang nucleosynthesis, and its predictions have been spectacularly confirmed by observation. Astronomers can measure the composition of ancient gas clouds and primordial material, and they find roughly 25% helium by mass in the universe, just what the theory of those first few minutes predicts. That congruence is a triumph of the Big Bang model. It shows that our understanding of the early universe's conditions is on the right track. If the universe had expanded or cooled at a much different rate, the yields of helium or deuterium would have been different. But the observed abundances match the idea of a hot, rapidly expanding early universe that cooled through the right temperature range for just long enough to produce helium in that amount. The forging of heavier elements stopped at this point. After about 20 minutes, the universe had expanded and cooled too much for further fusion. The nuclear fires of the Big Bang died down, leaving mostly light elements. There were no carbon, oxygen, or iron atoms yet. Those would come much later, inside stars. The universe at this stage was still a featureless hot bath of radiation and simple nuclei. But the chemical foundation was set. Everywhere, the same light elements in the same proportions. Later, when stars formed, they would build on this foundation, fusing helium into carbon and beyond. But the first bricks, hydrogen, helium, and a dash of lithium, were laid in those opening minutes of cosmic time. It's astonishing to think that in mere minutes after the beginning, the universe's broad chemical makeup was established. Every star that twinkles, and every breath we take, full of oxygen from stars, but hydrogen that dates back to the Big Bang, has roots in that early recipe. The lightest elements are direct relics of the Big Bang's fires, and their presence, measured today, is like a chemical memory of that era. With the basic ingredients of matter now in place, and the universe continuing to expand and cool, the stage was ready for structure to start emerging. But first, the universe had to get through a long, dark age. During that time, no stars yet existed, just diffuse gas gradually pulling together under gravity's guidance. The cosmos was dark, but not idle. Gravity was working slowly to gather the first galaxies. To uncover how the universe's expansion continued, and how we measure those enormous distances and the passage of time, we rely on certain natural beacons. These come in the form of exceptionally bright objects and patterns, standard candles and standard rulers that help us chart the cosmos. With the light elements in hand and darkness before the dawn of stars, our view shifts to how we map the expanding space and discover the subtle forces at play. It is time to ignite some cosmic candles in the dark and lay down measuring sticks across the universe's vastness. For a long stretch after the Big Bang's bright beginning, the universe had no stars. It was dark, filled with cooling gas, slowly assembling into protogalaxies. Eventually, the first stars kindled, and the cosmic darkness gave way to light once more. As galaxies began to shine, the cosmos offered natural tools to measure its own vastness. In the grand darkness of space, certain stars and stellar events serve as beacons, guiding lights that allow us to gauge distance and trace the expansion of the universe. Astronomers call these standard candles because their true brightness is known, making them reliable distance indicators. By comparing how bright they appear to us versus how bright they truly are, we can deduce how far away they must be. One of the most important standard candles is a kind of pulsating star known as a Cepheid variable. These stars rhythmically brighten and dim over a precise period, and that period is directly linked to the star's intrinsic luminosity. Early in the 20th century, Henrietta Swan Leavitt discovered this period luminosity relation. A Cepheid with a longer pulsation period is intrinsically brighter. With this calibration, astronomers can observe a Cepheid in a distant galaxy, measure its pulsation period. For example, it might brighten and dim over the course of, say, 30 days, and from that infer the star's actual luminosity. Comparing that to how faint it looks from Earth reveals the distance. Using Cepheids, Edwin Hubble was able to determine that the Andromeda Nebula was actually a faraway galaxy, not a nearby gas cloud, proving the universe extends beyond the Milky Way. Cepheids remain crucial standard candles, visible out to tens of millions of light-years, allowing us to chart the nearer cosmic neighborhood. For even greater distances, a more dramatic candle comes into play. The Type 1, a supernova. These are exploding stars that blaze with such intensity that they can be seen across billions of light-years. Remarkably, Type Ia supernovae reach almost the same peak luminosity in each explosion. They occur in binary star systems when a white dwarf star triggers a runaway fusion explosion. Because the conditions of these explosions are similar, the resulting supernova acts as a standardized light bulb of known wattage. When one erupts in a distant galaxy, we can measure its apparent brightness and gauge how far that galaxy is from us. In late 1998, observations of far-flung Type Ia supernovae provided the crucial evidence that the expansion of the universe is accelerating. Those supernovae appeared a bit dimmer and thus farther away than expected, revealing a surprising cosmic repulsion at work. But even aside from that revelation, supernovae have been key mileposts in constructing the distance ladder that reaches to the universe's grand scale. Beyond candles, the cosmos also offers standard rulers. Known size features whose apparent size or separation can be used to infer distance. One example we've already encountered is the imprint of those primordial sound waves, the baryon acoustic oscillations. That ripple pattern established a preferred scale, around 450 million light-years, in the clustering of galaxies. By looking at how large that pattern appears at different epochs, for instance, in the early universe's microwave background versus in the distribution of galaxies today, cosmologists can calculate how the universe's expansion has changed over time. The cosmic microwave background's spot patterns and the statistical clustering of galaxies both encode this standard ruler, allowing a cross-check on cosmic distances independent of light-based methods. Another kind of standard ruler is found in certain variable stars or other stable phenomena whose physical size is known. But by far, the most precise rulers for cosmology have been those derived from the large-scale structure itself, like the acoustic wave imprint, combining the distance estimates from standard candles like Cepheids and supernovae with those from standard rulers like the BAO scale, gives us a powerful grip on the cosmic distance scale. We essentially have both light and sound as our measuring tools. The pulsing of stars and the fossil ripples from the Big Bang. Together, They help build a three-dimensional map of the universe, indicating not just how far things are, but also how the expansion rate has changed at different times in cosmic history. Using these methods, scientists have constructed what's called the cosmic distance ladder, step by step, from nearby stars out to the edge of the visible universe. Parallax measurements gauge the distances to the closest stars. Cepheids extend from those stars to nearby galaxies. Supernovae leapfrog further, tying distances across billions of light years. And the large-scale clustering provides a handle on the truly vast scales. With each rung of this ladder, we refine our measurement of the universe's expansion rate, the Hubble constant, and gain insight into the dynamics at play. In fact, it was by using cepheids and supernovae that we discovered one of the most profound mysteries of modern cosmology, the realization that the expansion is accelerating due to an unknown force, a force now known as dark energy. The standard candles and rulers are like lighthouses and surveyor's rods in the cosmic ocean. They guide us across darkness, giving us distances and scales that would otherwise be far beyond our reach. With them, astronomers transformed the blurry scatter of galaxies into a calibrated framework, turning points of light into a coherent story of an expanding universe. By lighting these candles in the dark and laying down these rulers, we come to the startling observation. Not only is the universe expanding, but that expansion has an unexpected twist. As we move to the next part of our journey, we focus on that surprise, the gentle but persistent push that is speeding up the expansion of space itself. At the turn of the 21st century, our cosmic distance measuring tools unveiled an unexpected plot twist in the universe's story. Astronomers using Type Ia supernovae as standard candles peered deep into space, and thus far back in time, to measure how the expansion of the universe had proceeded. They expected to see signs that gravity had been slowing the expansion over billions of years. Instead, they found the opposite. Distant supernovae were dimmer than anticipated, indicating they were farther away than a steadily decelerating expansion could explain. In 1998, two independent teams announced this astonishing result. The expansion of the universe is speeding up. The cosmos, it turns out, is not just drifting apart, but doing so with ever-increasing pace, as if some mysterious late-time push is nudging galaxies apart more and more. This phenomenon was dubbed dark energy. Dark because its nature is unknown, it emits no light and cannot be seen directly, and energy because it seems to behave like a form of energy intrinsic to space itself. Dark energy is the name we give to whatever is causing this accelerated expansion. We observe its effect clearly in the motions of galaxies. Starting about 5 to 6 billion years ago, the expansion began to outrun the gravitational pull of matter. By today, roughly 13.8 billion years into cosmic history, dark energy dominates the cosmic energy budget, comprising about 68% of the total contents of the universe. It's as if empty space has an underlying propensity to expand, a subtle pressure that grows more influential as the universe grows older and emptier. One way to think of dark energy is as a kind of negative gravity or repulsive effect, though that's an oversimplification. In Einstein's theory of general relativity, energy and pressure can affect the expansion of space. A constant energy density filling space, something like Einstein's cosmological constant, would have a repulsive effect, causing expansion to accelerate. Einstein himself had once introduced such a term into his equations to achieve a static universe, then later discarded it when expansion was discovered, calling it a blunder. Little could he know that a form of this idea might actually describe the reality. A small positive cosmological constant, or vacuum energy, appears to be real and is pushing the universe outward. In other words, every cubic centimeter of space may contain a fixed amount of this energy, and as space expands, more space means more of this energy, exerting its repulsive influence. We don't yet know if dark energy is truly a constant property of space, or something more dynamic, like a field that changes over time, sometimes called quintessence. So far, all evidence is consistent with it being very close to constant, the simplest explanation. But the puzzle remains profound. The amount of dark energy observed is extraordinarily small in density, much less than any everyday matter or energy. Yet over the vast volume of the universe, it adds up to the dominant component. It's as if the fabric of the cosmos has a tiny built-in springiness that only becomes noticeable over enormous scales and long times. Over the first few billion years, matter with its gravity was the stronger influence and slowed the expansion. But as matter spread out and diluted, this mysterious energy of space became significant and gently took over, coaxing the expansion to speed up again. The effect of dark energy is extremely gentle. We don't feel space stretching locally in our daily lives or within galaxies. It only becomes apparent when you look across billions of light years. Over those immense distances, dark energy has been accumulating its influence, so we see galaxies today receding from each other faster than they were billions of years ago. It's not that galaxies have rockets on them. Space itself is doing the pulling. The term dark energy is, in a way, a placeholder, a signpost of our ignorance. We can describe its effects very precisely, but we haven't identified a particle or a force carrier behind it. It could be something deeply woven into the structure of space-time. It could even be a sign that our understanding of gravity needs modification on the largest scales. For now, we treat it as an energy inherent to space, a smooth field that permeates everything. The discovery of cosmic acceleration was met with astonishment and has been confirmed by multiple lines of evidence since. Not only supernovae, but also observations of the cosmic microwave background and large-scale structure, all point to an accelerating cosmos. We find ourselves in a universe that, in the far future, will likely be dominated by this repulsive effect. If dark energy remains constant, galaxies not gravitationally bound to us, like those outside our local group, will drift faster and faster beyond our observable horizon. Trillions of years hence, distant galaxies' light will fade away, leaving each remaining galaxy group isolated in a dark, empty expanse. This is the projected fate under the dark, energy-driven expansion. For now, though, in our epoch, dark energy's push is gentle, noticeable only through careful measurement. It has been poetically called the cosmic capriciousness, a twist that the universe unveiled late in its life. Understanding what dark energy actually is constitutes one of the greatest challenges in cosmology. Whether it is a property of the vacuum, a new dynamic field, or a sign of new physics, it reminds us that the cosmos still holds deep secrets. As we contemplate this unseen energy accelerating the expansion, we can't help but wonder about the limits of what we can observe and know. This brings us to consider how far our sight reaches and how time and space interplay at the edges of the universe. In other words, the horizons that bound our cosmic vision and the flow of time on the grandest scales. Ultimately, horizons remind us that we have limits in observing the cosmos. They are a fundamental feature of an expanding universe governed by relativity. They speak to the shape of time, how time and expansion together set a boundary on knowledge. Gazing out, we look into the deep past. Gazing far enough, we hit a wall beyond which the past remains forever out of reach. Yet within our horizon, we have managed to learn an astonishing amount about cosmic history by developing new ways of sensing the universe. Beyond just light, we continue to push those boundaries in different ways. Not all messengers are limited by the same horizons, and one new cosmic messenger has recently given us a way to hear events from deep in space, even those invisible in light. It's to this new sense, the whisper of space-time itself, that we now turn as we near the end of our journey. For generations, our knowledge of the cosmos came almost entirely from light. The electromagnetic waves, spanning radio to gamma rays, that travel to our telescopes. But the universe has more to tell us than what we can see. In recent years, we've gained the ability to sense a different kind of cosmic messenger. Gravitational waves, ripples in the very fabric of space-time. Predicted by Einstein's theory of general relativity over a century ago, these waves are produced by massive objects undergoing rapid acceleration. For example, two heavy stars or black holes spiraling into each other. When such cataclysmic events occur, they send out vibrations that stretch and squeeze space itself as they pass by. By the time these waves reach us, they are incredibly faint, smaller than an atom by the time they cross Earth. Yet with delicate instruments, we can now detect these whispers from across the universe. In September 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, made history by catching the first direct sound of spacetime's ringing. Two black holes, each about 30 times the Sun's mass, collided over 1 billion light-years away. For a brief moment, they released more energy in gravitational waves than all the stars in the observable universe were emitting in light. LIGO recorded the final fraction of a second of their dance, a rising chirp as the black holes drew together and merged. This observation confirmed that gravitational waves exist and opened a new window on the universe. It was as if we had been watching the cosmos in silence and suddenly gained the sense of hearing. We could literally listen to the collision of black holes in the dark. Gravitational waves carry information that light cannot. The black holes that produced that first detected signal emitted no light at all. Black holes are black after all. So without gravitational wave detectors, we would never know about the merger. Now we can detect events like two neutron stars crashing together, something LIGO and its European partner Virgo accomplished in 2017. That event not only sent gravitational waves but also light, a burst of gamma rays followed by afterglows, allowing astronomers to observe it with both senses and confirm that heavy elements like gold were forged in the collision of neutron stars. Gravitational waves, in that case, gave the first alert and precise location for telescopes to follow up. This marked the dawn of multi-messenger astronomy, where we use both electromagnetic and gravitational signals to get a fuller story of cosmic events. The sensitivity of gravitational wave observatories is astonishing. LIGO's two facilities in the US use laser beams along 4-kilometer arms to measure tiny distance changes caused by a passing wave. They can detect a change as small as 1 part in 1,000 trillion, akin to measuring a shift the size of a proton over kilometers. It has to be that sensitive because space-time is stiff. Even the most violent cosmic events produce only the gentlest whispers by the time they reach us. And yet, those whispers speak volumes. By analyzing the gravitational wave signal, scientists can deduce the masses of the merging objects, how fast they spun, and how far away the merger happened. It's a completely new kind of cosmic hearing. Looking ahead, this new sense will only improve. Plans are underway for space-based gravitational wave detectors, like the European LISA mission, which will listen to lower frequency waves from even more massive inspirals, such as supermassive black hole mergers. Pulsar timing arrays, another ingenious method, are using radio observations of pulsars, rapidly spinning neutron stars, to detect nanohertz gravitational waves from giant black holes slowly orbiting each other in distant galaxies. In June 2023, scientists announced the first hints of such a background hum of gravitational waves permeating the universe, likely from the cumulative rumble of many merging supermassive black holes. If confirmed, it means even the quiet, steady state of the cosmos carries the imprint of colossal slow dances of galaxies. We also dream of detecting primordial gravitational waves, faint murmurs from the time of inflation itself. These would be gravitational echoes of the Big Bang's immediate aftermath, still resonating today in the fabric of spacetime. Unlike light, which was trapped until the universe was 380,000 years old, gravitational waves could travel freely even in the earliest moments, so they hold the potential to show us aspects of creation we otherwise cannot see. Experiments are searching for subtle patterns in the polarization of the cosmic microwave background that would indicate these ancient gravitational waves. No definitive detection has been made yet, but the effort continues, and a future discovery would give us a direct window into the universe at fractions of a second old. In the meantime, each new gravitational wave detection expands our understanding. We have heard black holes merging, neutron stars colliding, and perhaps soon we'll detect white dwarf binaries in our galaxy humming to each other, or the distant chorus of supermassive black holes. Gravitational waves have truly become a new sense for astronomy, allowing us to both broaden and deepen the cosmic narrative. With them, the cosmos is no longer silent. We stand at the shore of a cosmic ocean of sound, just beginning to listen to its waves. As we conclude this part of our journey, we pause in the stillness after hearing these cosmic whispers. The universe, once invisible forces and silent movements, is becoming ever more alive with information through our expanding senses. We carry forward in our exploration, knowing that every answer raises new questions. The cosmos continues to unfold its unseen wonders, and our journey through the hidden forces shaping the universe goes on, ever deeper into the unknown, to the